Okay, welcome to this figure oil painting lesson. In this lesson you can see me paint this painting all the way from sketch to finished product. I also put in a Q&A in front of the video that you soon will see. Start soon. So good luck and hope you get something out of this because it took a while to make it. And see you at the end, I hope. Stay cool. Hello YouTube, it's me again. I sold the painting, which there are two videos of on YouTube, and it's this one over there. I just wanted to, because I'm sending this off next week to the new owner, and I just wanted to show you this one. Because I have two files on YouTube of this painting. It's called Victoria with Wild Red Rose. And one of the files, I actually did it quite 5 years ago, is seen 150 or 160,000 times by now. And it's by far the most popular video. It's a long video and it's not a really good quality either. Then there's another video from sketch to finished product, and you can watch me paint this painting. I will post links. I'll post links to the painting process videos on this side and that side, and yeah. Anyway, I want to just show you how I painted. It's kind of, I worked a lot with the paint, like clay-like, and that is how I make this quite sculptural effect. I like my paintings to kind of come out of the canvas. I'm not a photorealist. I actually like to build my paintings more like I would build a sculpture, which I also want to start doing. Work with clay and maybe even reliefs and stuff like that. So see what happens. I also want to learn to play the piano, but that might be a stretch. Anyway, when I paint, I think a lot about Rembrandt, how they created, or he created the textures. I also think about Vermeer, the fluidness of his paint, like some of them are almost like aquarelle. It has used the oil and the color in such a way that it actually feels like watercolor in some of the most beautiful paintings of him. So yeah, you can actually see my palette over there, and you can see that I use all the colors of the rainbow, from different yellows and over in the more darker ones, and then you have the blue ones, and yeah, so that's actually a palette I'm using today. And that's my studio. So anyway, that's why my paintings become quite vivid, because I use clean colors of the rainbow, and I'm fighting with that, because sometimes I feel it becomes too much, sometimes they become too vivid, too real, too much, even for me. But then again, people tell me I'm too much, so I guess it's in my genome or in my personality what comes out on the canvas. Anyway, this is what I do and what I love doing, so this is what I'm gonna keep doing for the rest of my life. Anyway, thanks for watching my videos, and if you want to support my channel, there are different ways you can do that. You can give my videos a thumbs up. Yay! You share them on social media. That's fantastic. and put them into your playlists on YouTube. And if you want to support me, you can also donate. There's a donate button on the channel, and there's also a link down here, I think, to my Patreon. So if you, I'm going to try to build up my Patreon and start posting videos and other stuff on Patreon. So with this, I thank you for watching. And remember to leave a comment, and I will answer you as fast as I see them. And if you have questions about painting and other stuff, you just ask me, and I will ask to my best ability. Okay, thanks for watching. Links there and there.
Why are we here? Where do we come from? These are the most enduring of questions, and it's an essential part of human nature to want to find the answers. Now we can trace our ancestry back hundreds of thousands of years to the dawn of humankind, but in reality our story extends far further back in time. Our story starts with the beginning of the universe. It began 13.7 billion years ago. And today it's filled with over 100 billion galaxies, each containing hundreds of billions of stars. In this series, I want to tell that story, because ultimately we are part of the universe, so its story is our story. The force at the heart of this story is gravity. This fundamental force of nature built everything we see. It creates shape and order, and it initiates patterns that repeat across the heavens. But gravity also forges some of the most alien worlds in the cosmos. Worlds that defy belief. The quest to understand this fundamental force of nature has unleashed a golden age of creativity, exploration and discovery. And it's led to a far deeper understanding of our place in the universe. Every moment of our lives, we experience a force that we can't see or touch. Yet this force is able to keep us firmly rooted to the ground. It is, of course, gravity. But despite its intangible nature, we always know it's with us.
I'm going to ask you, how do you know that there's gravity around here? And you might say, well, it's obvious, you know, I can just do an experiment, I can drop something. Well, yes, but actually, gravity is a little bit more subtle than that. But to really experience it, to understand it, you have to do something pretty extreme.
And this plane has been modified to help me do it. Thanks to its flight plan, it's known as the Vomit Comet. Once we've climbed 15,000 meters, this plane does something no ordinary flight would do. Its engines are throttled back and the jet falls to Earth. And then, something quite amazing happens. By simply falling at the same rate as the plane, for a few fleeting moments, we are all free of gravity's grip. But this isn't just a joyride.
Very profound here, because although I'm falling towards the ground, you see, gravity has completely gone away. Gravity is not here anymore. I've cancelled gravity out just by falling. If you understand that, then you understand gravity.
So it is possible, by the simple act of falling, to get a very different experience of gravity. But this force of nature does more than just bring us back down to Earth.
Gravity also plays a role on the grandest of stages, because across the universe, from the smallest mote of dust to the most massive star, gravity is the great sculptor that created order out of chaos.
Since the beginning of time, gravity has been at work in our universe. From the primordial cloud of gas and cosmic dust, gravity forged the stars. It sculpted the planets and moons and set them in orbit around the newly formed suns. And gravity connects these star systems together in vast galaxies and steers them on their journey through unbounded space.
Over the centuries, our quest to understand gravity has allowed us to explain some of the true wonders of the universe. But at a deeper level, that quest has also allowed us to ask questions about the origin and evolution of the universe itself.
To understand how gravity works across the universe, we need look no further than the ground beneath our feet.
Well, the first scientist to really think about it was Isaac Newton back in the 1680s. And he said this: gravity is a force of attraction between all objects. Now, the force of attraction between these two rocks is obviously very small, almost impossible to measure. And that's because the force is proportional to the masses of the objects. And these things are not very massive. But there is a more massive rock around here. So what I'm standing on, planet Earth.
The mass of our Earth generates a gravitational pull strong enough to sculpt the entire surface of the planet. It causes water to gouge out vast canyons.
It sets the limit for how high mountains can soar, and it shapes whole continents. But this invisible force does more than just shape our world. The skies are always changing. The constellations rise and fall in different places every night, and the planets wander across the background of the fixed stars. But throughout human history, there's been one constant up there in the night sky, because every human that's ever lived has gazed up at the moon and seen one face shining back at us. The reason why we never see the dark side of the moon is all down to the subtlety with which gravity operates. Millions of years ago, the moon rotated rapidly, but from the moment it was born, our companion felt the tug of gravity. Just as the moon creates great tides in our oceans, the Earth caused a vast tide to sweep across the surface of the moon. But this tide wasn't in water, it was in rock. Imagine that this is the moon, and over there is the Earth. The Earth's gravity acts on the moon and stretches it out into a kind of rugby ball shape. Now, the size of that tidal bulge facing the Earth is something like 7 meters in rock. And then as the moon rotates, that bulge sweeps across the lunar surface. I mean, imagine what that would look like here. You'd see a tidal wave sweep across this landscape with the rock rising and falling by 7 meters. This massive wave acted like a brake and gradually slowed the moon down. Eventually, the tidal bulge became aligned with the Earth, locking the speed of the moon's rotation. So the time it takes the moon to spin once is almost the same as the time it takes to orbit the Earth. So there is no dark side of the moon, just a side that gravity hides from our view. The bond that gravity creates between the Earth and the moon is repeated across the cosmos. It's the glue that holds the planets in orbit around the sun. And it binds our solar system and countless other solar systems together to form galaxies like our own Milky Way. But gravity's influence can be felt even further because it controls the fate of galaxies. When you look up into the night sky, then you see the universe as it looks in visible light, with the glowing of the stars and the galaxies. But that's only part of the story, because the universe is full of dust and gas, which you can't see with a conventional telescope, but you can see with a telescope like this. Radio telescopes, like the Very Large Array in New Mexico, are able to peer deep into space and reveal the incredible attractive power of gravity. This is Andromeda, a spiral galaxy roughly the same size and mass as the Milky Way. This island of over 1 trillion stars sits over 2.5 million light years away. But every hour, that gap shrinks by 500,000 kilometres. Whilst most galaxies have been rushing away from each other ever since they formed just after the Big Bang, some galaxies form so close together that they are locked in a gravitational embrace. Now the Milky Way and Andromeda are two such galaxies, and computer simulations suggest that they will collide together in around 3 billion years' time. And look at that. That's a simulation of the Milky Way galaxy and the Andromeda galaxy colliding together. And all these wisps of smoke getting thrown out are stars. And these are star systems getting ripped out of the galaxy and thrown off into interstellar space. These two islands of hundreds of billions of suns have flown through each other, and gravity has exerted its grasp and dragged them back again. And just remember that we are one of those dots. You know, our sun and the Earth and the solar system are either going to be flung out into interstellar space, or they're going to be in here in this maelstrom of hundreds of billions of suns swirling around each other and forming the core of a new galaxy. But just imagine what it would be like to gaze up at the sky as Andromeda approached. And the sky would be ablaze with the light of hundreds of billions of suns, and the imminent collision would provide the energy to generate the births of hundreds of millions more. And what a magnificent sight it would be. But far more magnificent is the immense scale of gravity's embrace. It holds galaxies together across hundreds of billions of kilometres, and in doing so, it creates the most magnificent structures. Our own Milky Way is part of one of these, the Virgo cluster. Every point of light in this image is not a star, but a galaxy. There are 2,000 galaxies in this cluster, and they are all bound together by gravity, making it the largest structure in our intergalactic neighbourhood. There seems to be no limit to the reach or power of gravity. Its influence can be felt across the vast expanses of space and time. But there's something very interesting about gravity, because it is by far the weakest force of nature. I mean, look, I can pick this rock up off the ground, even though there's an entire planet Earth, trying to pull it down. So, if gravity is so weak, how come it's so influential? Gravity may be weak here on Earth, but it's not so weak across the cosmos. This invisible force varies on all the planets in the solar system and on the exoplanets we've discovered orbiting other suns. To experience what gravity feels like on these worlds, I need to go for a spin. This is a centrifuge. It was built in the 1950s to test whether fighter pilots had the right stuff, but it's going to allow me to feel what it'd be like to stand on the surface of any of the planets in the solar system that are more massive than the Earth. And in fact, also what it'd be like to stand on some of the planets that we found around distant stars.
Right, I'll have to strap you in first of all. Let me see. This is a go-to-go switch. It's an emergency switch in case something happens and your release of the sensors will stop.
I was just told by the F-16 fighter pilot who's just been in here that it's 100 times more uncomfortable than being in a jet fighter. And I was kind of confident because I've been in jet fighters and didn't find it too uncomfortable, but apparently this is 100 times worse.
Doors closed again, protocols there, safe rooms are there, doctor is ready. We'll start up the centrifuge, Brian, and bring you in orbit. And it happens in 3, 2, 1 second from now.
The first planet I'm travelling to is Neptune. Its gravity is just fractionally stronger than here on Earth. This is the gravitational field on Neptune, and you feel, you know what, I could probably get used to this. I could probably live on the surface of Neptune.
Can you lift your hands a little?
There we go.
Yeah, and down.
And it is actually quite an effort. It is noticeably heavier. It's like having a reasonably heavy weight in your hand.
You're ready to go to 2.5 G?
Yeah, so now we'll move from Neptune to Jupiter.
Let's go there.
Jupiter is over 1,300 times more massive than the Earth, but because it's mostly gas, it's not very dense, so its gravity is just over twice as strong at its surface. Well, now actually it is quite difficult to lift my hand, and that's 2.5 G. I wouldn't want to sit here for half an hour.
And can you lift both of your hands above your head and see what happens there?
Let's see, so actually, just about, but actually it's an immense amount of hard work. So it would be hard work living on Jupiter.
Let's go to 4G.
Actually, this is heading to a planet around a planet called Ogle 2 TR-L9b, which is around a star in the constellation of Carina. It's one of the exoplanets we've discovered. Oh, there we go. Now that is actually beginning to feel quite unpleasant.
Can you describe what you're feeling?
A very heavy face.
Alright.
My head is extremely heavy.
How about your lungs? Inhaling, exhaling, breathing?
It's much harder work. I can't lift my hand off my leg.
Okay.
And that's at 4G.
Yeah.
But my head and my face feel very, very heavy.
Yeah.
It's quite an unpleasant feeling.
We'll go to 5 and let me know if you have any visual disturbances.
I'm now en route to a newly discovered exoplanet, WASP-8b. 4.4. This world sits in the small and faint constellation of Sculptor. Quite hard to speak. It has a gravitational force nearly 5 times that of the Earth.
Alright, we'll go to 5G.
Oh, very foggy.
Okay.
Very foggy.
Very foggy. Still foggy?
Yeah.
Alright.
Take it down.
Okay, we'll take you down.
face felt a bit saggy though.
Well, you looked a little different.
Quite unpleasant at the time actually. So it went very quickly up to 5G. And what happens is, well for me anyway, this vision becomes very, very foggy. Just the whole thing just blurs and blurs and blurs. So you realise that we're obviously very finely tuned to live on a planet that has an accelerated reduced gravity of 1G. When you go to 2G, it's difficult. When you go to 3G and 4G, it becomes unpleasant. And 5G, anyway, for me, was on the border of being so unpleasant that you pass out. So although gravity feels weak here on Earth, it certainly isn't weak everywhere across the universe. And that's because gravity is an additive force. It scales with mass, so the more massive the planet or star, the stronger its gravity. The body with the strongest gravity in our solar system is the Sun. Our star has so much mass packed inside a relatively small space that it has a gravitational pull at its surface 28 times that of the Earth. If I were able to set foot on this world, all the blood would be pulled out of my upper body, and I would die in less than a minute. But our Sun's gravitational force is nothing compared to the extreme G found at the surface of one of the strangest places in the universe. Imagine the gravity on a world with more mass than our Sun, crammed into a sphere just 20 kilometres across. We first detected such a wonder just 40 years ago, but the story of its discovery begins over 1,000 years earlier. This is Chaco Canyon in New Mexico in the southwestern United States, and it was home to what's become known as the Chacoan civilization. Well, this is Pueblo Bonito, one of the so-called Chacoan Great Houses. Now, back in the 1100s, this place had over 600 rooms. It's thought that this building must have been ceremonial or religious, a cathedral, if you like. The Chacoan Great Houses are aligned with interesting objects in the sky, so the point at which the sun and moon rise at important times of the year. So it seems that by constructing these grand buildings, the Chacoans were not only trying to place themselves at the heart of local culture, but also to place themselves at the heart of the cosmos. Very little is known about the Chacoan culture because no written text has ever been discovered. But in another part of the canyon, there is a record of a spectacular event that they witnessed in the sky in 1054. I've known about this place since I was about 12 or 13 years old, and the reason is this book and the television series Cosmos, Carl Sagan's masterpiece,
probably the most important reason that I got interested in astronomy. On page 232, there's a picture that's always fascinated me, captured my imagination, and it's a photograph of that wall of rock, and in particular, a painting that's on the overhang, because it's thought that that painting is a record of one of the most spectacular and magical events in the cosmos.
On July 4th, 1054 AD, a bright new star appeared, and it outshone every other star in the night sky for over 3 weeks. It was so bright that it was visible in the daytime. And it's thought that this painting is the Chacoan people's record of that astronomical event. And the reason we think that is that using modern computer techniques, you can wind back the night sky and say, where would the moon have been? Where would the stars have been? And you find that in that direction, the moon would have risen and tracked across the night sky, and the new star would have been very, very close to the crescent moon. We now know that that new star was in fact the explosive death of an old star, a supernova explosion, a star literally blowing itself apart at the end of its life. Throughout a star's life, there is a constant battle between energy pushing out and gravity pushing in. As long as the star burns, the two forces balance each other out. But when it runs out of fuel, gravity wins, and the star collapses and then explodes with the brightness of 1 billion suns. We can no longer see the supernova that Chacoans saw, but we can still marvel at what it left behind. This is the Crab Nebula, the remains of that exploding star that the Chacoans saw in these skies 1,000 years ago. It's an expanding cloud of gas and dust, the remains of that dying star. The colours are different chemical elements, so the orange is hydrogen, the red is nitrogen, and those filaments of green are oxygen. While the explosion blew most of the stellar material out into the cosmos to form this vast nebula, we now know that this wasn't the end of the story. At the centre of the nebula lies the remnant of the star, its core crushed by the force of gravity. That is a neutron star, an image taken by the Chandra X-ray satellite. Central blob there is only about 20 kilometres across, but it's got the mass of our sun, a star the size of a city. It's spinning at a rate of over 30 times a second, 1,800 revolutions per minute, and it really is an astonishingly alien world. As the neutron star spins, jets of particles stream out from the poles at almost the speed of light. These jets are powerful beams that sweep around as the star rotates. When the beams sweep across the Earth, they can be heard as regular pulses, so we call them pulsars. But it's not this rhythmic noise that makes the crab pulsar a wonder. It's the extraordinary nature of gravity on this alien world. if I were to be on its surface, then the gravitational pull on me would be 100,000 million times that I feel on Earth. That means that if I were to jump from the top of that projection screen, and by the time I hit the ground, I'd be travelling at over 4 million miles an hour. That's a lot of gravity.
Pulsars have such extreme gravity because they're made of incredibly dense matter. To understand why, we have to look at what gravity can do to matter at the very smallest scales.
Everything in the universe is made of atoms, and until the turn of the 20th century it was thought that they were the smallest building blocks of matter. I mean, the word itself comes from the Greek atomos, which means indivisible. But we now know that atoms are made of much smaller stuff. Atoms consist of an atomic nucleus surrounded by a cloud of electrons. And whilst almost all of the mass is contained in the nucleus, it is incredibly tiny compared to the size of an atom. And if this were a nucleus, then the cloud of electrons would stretch out to something like 1 kilometre away. I mean, that's from here to that rock. And electrons on this scale are incredibly tiny. They're just like specks of dust, and there aren't many of them. So imagine a giant sphere centred on the atomic nucleus, stretching out all the way to that rock and beyond, with just a few points of dust in it. That's an atom. So that means that matter is almost entirely empty space. I'm full of empty space. The Earth is full of empty space. Everything you can see in the universe is pretty much just empty space.
So if everything in the universe is made up of atoms, and atoms are 99.9999% empty space, then most of the universe is empty. But in the Crab pulsar, the force of gravity is so extreme that the empty space inside the atoms is squashed out of existence. So all you're left with is incredibly dense matter.
Imagine this was matter taken from a neutron star, then it would weigh more than Mount Everest. Or, to put it another way, if I took every human being on the planet and squashed them so they were as dense as neutron star matter, then we would all fit inside that. And if I were to drop my neutron star stuff to the ground, then it would slice straight through the earth like a knife through butter.
Wherever we look in the universe, we see gravity at work. It creates shape and structure. It governs the orbits of every planet, star, and galaxy in ways we thought we were able to predict. But there was a flaw in our understanding of this force, and it was exposed by one of our close neighbours. This is Mercury. For thousands of years we've marvelled as this fleet-footed planet races across the face of the sun. But 150 years ago, astronomers noticed something strange about Mercury's orbit.
Imagine that this rock is the sun, and this is Mercury. Now Mercury has quite a complex orbit. For one thing, it's not a perfect circle, it's quite an elongated ellipse. So its closest approach to the Sun, it's around 46 million kilometres away, and then it drifts out to something just under 70 million kilometres. But you can calculate Mercury's orbit very precisely using only Newton's laws of gravity. So astronomers used to predict the exact time when you could look up into the sky, look at the Sun, and see the tiny disk of Mercury pass across its face. The thing was, they never got it right. They predicted it time and time again, and every time it happened, they got it slightly wrong, which was an immense embarrassment. So what they did was that rather than question Newton, they invented another planet, and they called it Vulcan. And they said that there must be another planet somewhere in the solar system which is always invisible from Earth, but which perturbed Mercury's orbit a bit. And so that was the reason their calculations were wrong. For decades, astronomers searched and searched for Vulcan. But they never found it, because Vulcan didn't exist. The explanation, the real explanation, was even more interesting than inventing the planet Vulcan, because it required a modification, in fact, a complete rewriting of Newton's law of gravity. Gravity is not a force pulling us towards the centre of the Earth like a giant magnet. In a sense, gravity isn't really a force at all. Describing the nature of gravity turned out to be one of the great intellectual challenges. But almost 200 years after Newton's death, a new theory emerged. The new theory, called general relativity, was published in 1915 by Albert Einstein after 10 years of work, and it stands to this day as one of the great achievements in the history of physics. See, not only was it able to explain with absolute precision the strange behaviour of Mercury, but it explains to this day everything we can see out there in the universe that has anything to do with gravity. And, most importantly of all, it explains how gravity actually works. Gravity is the effect that the stars, planets and galaxies have on the very space that surrounds them. According to Einstein, space is not just an empty stage, it's a fabric called space-time. This fabric can be warped, bent and curved by the enormous mass of the planets, stars and galaxies. You see, all matter in the universe bends. The very fabric of the universe itself. Matter bends space. I bend space. These mountains bend space, but by the tiniest of amounts. But when you get onto the scale of planets and stars and galaxies, then they bend and curve the fabric of the universe by a very large amount indeed. And here is the key idea. Everything moves in straight lines over the curved landscape of space. Everything moves in straight lines over the curved landscape of space-time. So what we see as a planet's orbit is simply the planet falling into the curved space-time created by the huge mass of a star. This is able to explain Mercury's erratic orbit. Because of the planet's proximity to our Sun,
The effects of the curvature of space-time matter far more for Mercury than for any other planet in the solar system.
But this idea of curved space is difficult to imagine, but we can only step outside of it. We can only float above space-time and look down on it. This is what our universe would look like.
You would see the mountains and valleys. You would see the little peaks and troughs created by planets and moons. And you would see these vast, deep valleys created by the galaxies. And you would see planets and moons and stars circling the peaks as they follow their straight line paths through the curved landscape of space-time. So one way to think about gravity is that everything in the universe is just falling through space-time.
The moon is falling into the valley created by the mass of the Earth. The Earth is falling into the valley created by the Sun, and the solar system is falling into the valley in space-time created by our galaxy. And our galaxy is falling towards other galaxies in the universe.
Einstein's theory of general relativity is so profound, so beautiful, that it can describe the structure and shape of the universe itself. But remarkably, the theory can also predict its own demise, because it predicts the existence of objects so dense, so powerful, that they warp and stretch and bend the structure of space-time so much that they can stop time, and that they can swallow light. These are objects so powerful that they can tear all the other wonders of the universe apart. Since the dawn of civilization, we've peered at the stars in the night sky and tracked the movements of the planets. We see these familiar patterns repeated across the whole universe. But when we train our telescopes to the stars that orbit around the centre of our galaxy, we see something very unusual. Well, this is one of the most fascinating and important movies made in astronomy over the last 10 or 20 years. This is real data. Every point of light in this movie is a star orbiting around the centre of our galaxy. They're known as the S-stars. Now, our Sun takes around 200 million years to make its way around the Milky Way. One of these S-stars takes only 15 years to go around the centre of the galaxy. It's travelling at 3,000 or 4,000 kilometres per second. Now, by tracking the orbits, it's possible to work out the mass of the thing at the centre. The answer took astronomers by surprise, I think it's fair to say, because the object in the centre of our galaxy is 4 million times as massive as the Sun, and it fits into a space smaller than our solar system. Now, there's only one thing that anyone knows of that can be so small and yet so massive, and that's a black hole. So what we're looking at here is stars swarming like bees around a supermassive black hole at the centre of the Milky Way galaxy. We think black holes can be smaller than an atom or 1 billion times more massive than our sun. Some are born when a star dies. When a star around 15 times the mass of our sun collapses. All the matter in its core is crushed into an infinite void of blackness known as a stellar mass black hole. Black holes are the most extreme example of warped space-time. They have such enormous mass crammed into such a tiny space that they curve space-time more than any other object in the universe. The immense gravitational pull of these monsters can rip a star apart. They tear matter from its surface and drag it into orbit. This superheated matter spins around the mouth of the black hole, and great jets of radiation fire from the core. Although these jets can be seen across the cosmos, the core itself remains a mystery. Black holes curve space-time so much that nothing, not even light, can escape. So their interior is forever hidden from us. But because we understand how matter curves the fabric of space, it is possible to picture what is happening.
Near a black hole, space and time do some very strange things, because black holes are probably the most violent places we know of in the universe. This river provides a beautiful analogy for what happens to space and time as you get closer and closer to the black hole.
Now upstream the water is flowing pretty slowly. Let's imagine that it's flowing at 3 kilometers per hour and I can swim at 4. So I can swim faster than the flow and can easily escape.
But as you go further and further downstream towards the waterfall in the distance, the river flows faster and faster. Imagine I was decide to jump into the river just there on the edge of the falls. The water is flowing far faster than I could swim. So no matter what I did, no matter how hard I tried, I would not be able to swim back upstream. I would be carried inexorably towards the edge and I would vanish over the falls. Well, it's the same close to a black hole, because space flows faster and faster and faster towards the black hole. Literally, this stuff, my space that I'm in, flowing over the edge into the black hole. And at a very special point, called the event horizon, space is flowing at the speed of light into the black hole. Light itself, travelling at 300,000 kilometres per second, is not going fast enough to escape the flow, and light itself will plunge into the black hole.
Well, as you fall into a black hole across the event horizon, then if you were going feet first, your feet will be accelerating faster than your head. So you would be stretched, and you would be quite literally spaghettified. Now as you get right to the centre, then our understanding of the laws of physics breaks down. Our best theory of space and time, Einstein's theory of general relativity, says that space and time become infinitely curved, that the centre of the whole becomes infinitely dense. That place is called a singularity, and it is the place where our understanding of the universe stops. Gravity is the great creator, the constructor of worlds. That's because it's the only force in the universe that can reach out across the vast expanses of space and pull matter together to make the planets, the moons, the stars, and the galaxies. But gravity is also the destroyer, because it's relentless, and for the most massive objects in the universe, for the most enormous stars and the centres of galaxies, gravity will eventually crush matter out of existence. Now the word beautiful is probably overused in physics. I probably overuse it. But I don't think there is any scientist who would disagree with its use in the context of Einstein's theory of gravity. Because here is a theory that describes a universe that is bent and curved out of shape by every moon, every star, and every galaxy in the sky. But I don't think there is any scientist who would disagree with its use in the context of Einstein's theory of gravity. Because here is a theory that describes a universe that is bent and curved out of shape by every moon, every star, and every galaxy in the sky. And everything in the universe has to follow those curves, from the most massive black hole to the smallest mote of dust, even to beams of light. But the most tantalising thing about Einstein's theory of gravity is we know that it's not complete. We know that it's not the ultimate description of the structure and shape of the universe. And that, for a scientist, is the most beautiful place to be, on the border between the known and the unknown. That is the true wonder of the universe. There's so much more left of it to explore.
Van Gogh's The Theory, here on BBC HD tomorrow at 8. And coming up next tonight, exploring a betrayal of trust on an epic scale with the story of former priest Brendan Smith. Next.
Why are we here? Where do we come from? These are the most enduring of questions, and it's an essential part of human nature to want to find the answers. We can trace our ancestry back hundreds of thousands of years to the dawn of humankind, but in reality, our story extends far further back in time. Our story starts with the beginning of the universe. It began 13.7 billion years ago. And today, it's filled with over 100 billion galaxies, each containing hundreds of billions of stars. In this series, I want to tell that story, because ultimately, we are part of the universe. So its story is our story. This film is about the stuff that makes us and where it all came from. Because understanding our own origins means understanding the lives of stars and how their catastrophic deaths bring new life to the universe. Because every mountain, every rock on this planet, every living thing, every piece of you and me was forged in the furnaces of space. In the Nepalese capital city of Kathmandu, and Hindus come here from all over India and Nepal to worship the god Shiva. In fact, that is Shiva's temple. Now, Shiva is the god of destruction. In the Hindu faith, everything has to be destroyed so that new things can be created. And that's why pilgrims come here to the banks of the Bagmati River at the foot of Shiva's temple. The belief in this cycle of creation and destruction lends Pashupatinath an added significance. Many of these pilgrims will have come here at the end of their lives, to die here and be cremated. Hindus believe in reincarnation, an eternal sequence of death and rebirth. Cremation helps free the soul so it's ready for the next life. They also believe that the physical elements of the body are released back to the world so they can be recycled in the next stage of creation. It's an ancient belief that touches on a deeper truth about how the universe works. Every civilization, every religion across the world has a creation story. It tells of where we came from, of how we came to be here, and of what will happen when we die. Well, I have a different creation story to tell, and it's based entirely on physics and cosmology. Now, it can tell us what we're made of and where we came from. In fact, it can tell us what everything in the world
is made of and where it came from. It also answers that most basic of human needs to feel part of something much bigger. Because to tell this story, you have to understand the history of the universe. And it teaches us that the path to enlightenment is not an understanding of our own lives and deaths, but the lives and deaths of the stars. My creation story is the story of how we were made by the universe. It explains how every atom in our bodies was formed not on Earth, but was created in the depths of space through the epic life cycle of the stars. And to understand that story, we will journey to the stars in all their stages of life. This is where stars are born, a nebula, a stellar nursery where new stars burst into life. Those stars will burn for billions of years until their voracious hunger for fuel forces them to blow up to become giants. Hundreds of times the size of our sun. And when they die, stars go out with the biggest bang in the universe. But to understand how we came from the stars, we must begin our journey much closer to home. Sunrise over Nepal, and those are the tallest mountains in the world, the Himalayas. I mean, every one of those peaks is over 6,500 metres. What a spectacular sight. But it's incredible to think that just a few tens of millions of years ago, those mountains were something very different. The Himalayas haven't always been mountains. We can find clues to their true origin by looking at them more closely. This is Himalayan limestone, the rock out of which much of this magnificent mountain range is made. Now, if you look closely, you can see a kind of chalky, granular structure, because limestone is made primarily out of the bodies, the shells of dead sea creatures, coral and polyps. And when they die, they're put under immense pressures and squashed and eventually form limestone. So the Himalayas were once living creatures. Much of the rock in the Himalayas was formed at the bottom of an ocean, and then over millions of years it was raised up to become these vast peaks. We've even found fossils at the top of Mount Everest. It's a beautiful example of the endless recycling of the Earth's resources that has been going on since the dawn of time. And we are part of that system. Every atom in my body was once part of something else. So an ancient tree, or a dinosaur, or a rock. In fact, definitely a rock. And the reason that the rocks of the earth can become living things, and then living things will return to the rocks of the earth, is because everything's made of the same basic ingredients. Those ingredients are the chemical elements, the building blocks of everything on earth. Elements like hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, sodium, magnesium. everything in the world is made up of the same basic set of chemical elements, just assembled in different ways. So these mountains, the Himalayas, are made of limestone, and that's calcium carbonate. Now, calcium, carbon and oxygen are three of the elements that are vital for life. So calcium in my teeth and bones, oxygen in the air that I breathe, and carbon in every organic molecule in my body. Now, you're probably pretty familiar with those elements in their combined forms, but you very rarely see the elements on their own.
There's a good reason why many of the elements are not found in their raw forms in nature. They're extremely reactive.
This is sodium. As you can see, it's a silvery metal, and it's also quite reactive. In fact, it's so reactive that when you drop it into water, you get a violent, almost explosive reaction, which is all the more surprising when you think that when combined with chlorine, this forms sodium chloride, salt, which is vital for life. Excellent. And that's why I love chemistry almost as much as physics.
It's this reactivity that enables the elements to combine with one another to make new substances.
What the hell's it doing?
That, in turn, has allowed the Earth to develop its endless variety. And that variety includes us. So to explain where we come from, we must also explain where the elements come from.
We now know that the Earth is made of 92 chemical elements. And that's pretty amazing if you think of the complexity that we see around us. We also know that everything beyond Earth, everything we can see in the universe, is made of those same 92 elements. And notice that I didn't say we think that that's what they're made of. I said we know that's what they're made of, because we can prove it.
The chemistry set we have on Earth extends far beyond the planet. We've set foot on the moon and know that it's rich in helium, silver and water. We've sent robot landers to our neighbouring planets and discovered that Mars is rich in iron, which is combined with oxygen to form its familiar rusty red colour. And we know that Venus's thick atmosphere is full of sulphur. We've sent spacecraft to the edge of the solar system to discover that Neptune is rich in organic molecules like methane. But what of the rest of the universe? It seems impossible that we could discover what the stars are made of, because they're so far away. Even the nearest star, Proxima Centauri, is 10,000 times more distant than Neptune, 4.2 light years from Earth. And the nearest galaxy, Andromeda, is another 2.5 million light years away. Yet despite these vast distances, these alien worlds are constantly sending us signals, telling us exactly what they're made of.
Our only contact with the distant stars is their light that's journeyed across the universe to reach us, and encoded in that light. Our only contact with the distant stars is their light that's journeyed across the universe to reach us, and encoded in that light is the key to understanding what the universe is made of. And it's all down to a particular property of the chemical elements. You see, when you heat the elements, when you burn them, then they give off light. And each element gives off its own unique set of colours. So this is strontium, and it burns with a Beautiful red colour. Sodium is yellow. Potassium is lilac. And copper is blue. Each element has its own characteristic colour. It's this property that tells us what the stars are made of. But it's a little more complicated than simply looking at the colour of the light that each star emits. You can see why by looking at the light from our nearest star, the Sun. This is a spectrum of the light taken from our Sun. And at first glance it looks very familiar. It looks like a stretched out rainbow, because that's exactly what a rainbow is. It's the spectrum of the light from the Sun in the sky. But if you look a bit more closely, then you see that this spectrum is covered in black lines. These are called absorption lines. Each element within our Sun not only emits light of a certain colour, it also absorbs light of the same colour. By looking for these black lines in the Sun's light, we can simply read off a list of its constituent elements, like a barcode. For example, these two black lines, in the yellow bit of the spectrum, sodium, you can see iron. Right down here, you can see hydrogen. So, by looking at these lines in precise detail, you can work out exactly what elements are present in the Sun. And it turns out that that's about 70% hydrogen, 28% helium, and 2% the rest. And you can do this not only for the Sun, but for any of the stars you can see in the sky, and you can measure exactly what they're made of. So that star there is Polaris, the pole star, and you can see that because all the other stars in the night sky appear to rotate around it. Now it's 430 light years away. But we know just by looking at the light that it has about the same heavy element abundance as our Sun. But it's got markedly less carbon and a lot more nitrogen. And the same applies for other stars. Vega, the second brightest star in the northern sky, has only about a third of the metal content of our Sun. Whereas other stars are metal heavy. Sirius, the dog star, contains 3 times as much iron as the Sun. And Proxima Centauri is rich in magnesium. But although the quantities of the elements may vary, wherever we look across space, we only ever find the same 92 elements that we find on Earth. We are made of the same stuff as the stars and the galaxies. But where did all this matter come from? And how did it become the complex universe we see today?
In order to understand where we came from, we have to understand events that happened in the first few seconds of the life of the universe. So when the universe began, it was unimaginably hot and dense. I mean, we literally don't have the scientific language to describe it. But it was, in a very real sense, beautiful. And there was no structure, certainly no matter. It was exactly the same, whichever way you look at it.
we can get some idea of how the universe developed from this state of pure symmetry by looking at the behaviour of water in this remarkable landscape. These are the Altatio geysers, high in the Chilean Andes. As the boiling water bubbles up through the ground to meet the freezing mountain air, water can be found in all three of its natural phases: vapour, liquid and ice. In its hottest state, water is, like the early universe, an undifferentiated cloud. But as it cools, it suddenly behaves very differently.
You see, if you look at a cloud of steam, it looks the same from every direction. But as it cools down, as it lands on this plate of freezing cold glass, then it immediately crystallises out, it turns into solid water, ice.
As the ice crystals form, the symmetry of the water vapour disappears from view, and complex, beautiful structure emerges.
In the same way, we think that the universe, as it cooled, went through a series of these events where structure emerged. One of the most important was about 1 billionth of a second after the Big Bang.
In that moment, an important part of the symmetry of the universe was broken. Known as electroweak symmetry breaking, this was the moment when subatomic particles acquired mass, substance, for the first time. Amongst them were the quarks. As the universe continued to cool, those quarks joined together to form larger, more complex structures called protons and neutrons.
Way before the universe was a minute old, the quarks had been locked away inside the protons and the neutrons, and they are the building blocks of all atomic nuclei, the building blocks of the elements.
These same protons and neutrons are with us to this day. They form the hearts, the nuclei, of all atoms. Just a few seconds after the beginning of the universe, the fundamental building blocks of everything had been created.
Well, it sounds ridiculous, you know, the fact that everything you need to make up me and everything on planet Earth, and in fact every star and every galaxy in the sky was there after the first minutes in the life of the universe. It's almost unbelievable, but we have extremely strong experimental evidence to suggest that that is the way that it is. But from that point on, it was just, in a sense, a process of assembling those bits into more and more complex things. That is an incredibly fascinating story in itself.
To tell that story, we must look deep inside the atom, to the nucleus at its centre. Here, we can see how protons and neutrons are assembled to build up the 92 different elements.
Now, the wonderful thing about the construction of the chemical elements is that it's so simple. I suppose you could call it child's play. So imagine these bubbles are my universal chemistry set. And then single bubbles are just be single protons. That's the nucleus of the simplest chemical element. The element with a single proton in its nucleus is hydrogen. And from hydrogen, you can make all the other elements. The first stage is to stick two protons together. Look at that! That was two bubbles stuck together. Now what happens when you stick two protons together is one of the protons turns into a neutron. Now that is called deuterium. Deuterium is still a form of hydrogen because it has only one proton in its nucleus. And it's the number of protons that defines the element. It's only when two deuterium nuclei are combined that a new element is created. Take two deuteriums and fuse them together, and you get a nucleus with two protons and two neutrons. That's helium, the second simplest element. And then it's just a question of adding more and more protons and neutrons. Well, there's an incredibly complicated nucleus. That's about 12 things stuck together. So that would be probably carbon 12, which is 6 protons and 6 neutrons. And you can carry on building more and more complex elements all the way up to the heaviest element in the universe, to uranium and beyond. Simple and beautiful physics. This process of building the elements is called nuclear fusion. It allows the simplest of ingredients to create the infinite variety of the universe. But although this bubble metaphor makes creating new elements seem simple, it is in reality incredibly difficult to achieve. So difficult that there's only one place in nature that it happens. It's in stars like our sun that the elements are assembled. They are the only places in the universe hot enough and dense enough to fuse atoms together. Even then, only a fraction of the star reaches the extreme temperatures necessary. The sun is 6,000 degrees Celsius at its surface, not nearly hot enough to power fusion. But deep below, where the temperature reaches 15 million degrees, the sun fuses hydrogen into helium at a furious rate. Every second, it burns 600 million tons of hydrogen. As it does so, it releases the huge amounts of heat and light that brings our planet to life. It is this process of converting that allows us to exist. For all its power, the sun only converts hydrogen, the simplest element, into helium, the next simplest. But there are over 90 other elements present in our universe. So where did they all come from? If the heavier elements are not being made in stars like the sun, then there must be somewhere else in the universe where they are assembled. It's important to know, because it's the elements beyond helium that give our world its complexity. And when it comes to planet Earth and human beings, there's one element that is particularly important: carbon. Life is completely dependent on carbon. I mean, I'm made of about 1 billion carbon atoms, as is every human being out there, every living thing on the planet. Imagine how many carbon atoms that is. So where does all that carbon come from? Well, it comes from the only place in the universe where elements are made: stars.
But in order for us to live, a star must die. Stars in the prime of their lives, like our sun, are only hot enough to make helium. Forming the heavier elements requires much higher temperatures. Temperatures that can only be reached at the end of a star's life. Looking out into space, you might think that the cosmos is a constant, unchanging place, that the stars will always be there. But in fact, the stars are only a temporary feature in the sky, and though they may burn brightly for many millions or billions of years, they can only live for as long as they have a supply of hydrogen to burn. When a star runs out of hydrogen, it begins to die. But it doesn't go quietly. Rather than cooling, the star becomes much hotter until there's a sudden flash. Then the star starts to expand. Over tens of thousands of years, it balloons to many hundreds of times its previous size. But in this bloated state, the star is unable to maintain its surface temperature. As it cools, it takes on the characteristic colour of a dying star. It has become a red giant. These are pictures of a red giant star in our galaxy, a star called Betelgeuse. Now, it's one of our nearest neighbours in cosmic terms. It's only about 600 light years away. But it's the size that's astonishing. Maybe to put the sun there, then Venus would be back there, and the Earth back there, and Mars here. And in fact, you could fit everything in the solar system all the way out to Jupiter, inside the star. Now, because it's so big, even though it is 600 light years away, you can see detail on its surface. So these are sunspots on the surface of Betelgeuse. But it's not what's going on the surface that's really interesting. To understand where carbon comes from in the universe, we have to understand what's going on deep in the heart of the star. Imagine this old prison in Rio is a dying star like Betelgeuse. There is the bright surface shining off into space. As I descend deeper and deeper into the prison, the conditions will become hotter and hotter and denser, until down there in the heart of the star is the core, and it's in there that all the ingredients of life are made. Deep in its core, the star is fighting a futile battle against its own gravity. As it desperately tries to stop itself collapsing under its own weight, new elements are made in a sequence of separate stages. Stage 1 is while there is still a supply of hydrogen to burn. Whilst the star's burning hydrogen to helium in the core, vast amounts of energy are released, and that energy escapes, literally creating an outward pressure which balances the force of gravity and holds the star up and keeps it stable. But eventually, the hydrogen in the core will run out, and at that point, the fusion reactions will stop, no more energy will be released, and that outward pressure will disappear. Now, at that point, the core will start to collapse very rapidly, leaving a shell of hydrogen and helium behind. Beneath this shell, as the core collapses, the temperature rises again, until at 100 million degrees, stage 2 starts, and helium nuclei begin to fuse together. A helium fusion does two things. Firstly, more energy is released, and so the collapse is halted. But secondly, two more elements are produced in that process. Carbon, oxygen, two elements vital for life. So this is where all the carbon in the universe comes from. You know, every atom of carbon in my hand, every atom of carbon in every living thing on the planet was produced in the heart of a dying star. Now, compared to the lifetime of the star, the creation process of carbon and oxygen is over in a blink of an eye, because in only about 1 million years the supply of helium in the core is used up. And for stars as massive as the Sun, that's where fusion stops, because there isn't enough gravitational energy to compress the core any further and restart fusion. But for massive stars like Betelgeuse, the fusion process can continue. When the helium runs out, gravity takes over again, and the collapse continues. The temperature rises once more, launching stage 3, in which carbon fuses into magnesium, neon, sodium and aluminium. And so it goes on. Core collapse, followed by the next stage of fusion to create more elements. Each stage hotter and shorter than the last. And eventually, in a final stage that lasts only a couple of days, the heart of the star is transformed into almost pure iron, whose chemical symbol is Fe. And this is where the fusion process stops. In its millions of years of life, the star has made all the common elements. The stuff that makes up 99% of the Earth. The core is now a solid ball of those elements, stacked on top of each other in layers. On the outside, there's a shell of hydrogen. Beneath it, a layer of helium. Then carbon and oxygen, and all the other elements, all the way down to the very heart of the star. And once that has fused into solid iron, the star has only seconds left to live. When a star runs out of fuel, then it can no longer release energy through fusion reactions. And then there's only one thing that can happen. In about the same amount of time it takes this prism block to crumble, the entire star falls in on itself. This is the destiny that awaits most of the stars in the universe. Yet even the implosion of a star only forges the first 26 elements. What of the remaining elements, some of which are vital for life, and many of which we hold most precious? These are the remote forests of Northern California. 100 years ago, this whole area was teeming with people, all in search of one element. And the reason they were here can still be found in the original 16:1 mine. This one stood at the centre of the California gold rush, and thanks to a quirk of geology, it continues to yield its precious bounty over 100 years later.
Now, the unique thing about this place is that it sits right on the divide between the North American plate and the Pacific plate. You see a divide there between the rock and quartz, and right up there you can see the top of it. Now, in between the faults, this rock, the quartz, formed about 140 million years ago in the Jurassic period, when the dinosaurs were running around above our heads. Hot water welled up and flowed. And that water deposited the gold through the seams of quartz. And so all the miners have to do, all they have to do, is follow the seams of quartz. And over hundreds of years, they found vast amounts of gold deposited there. Well, this is what all the fuss is about. This is the gold as it comes out of the ground, and it's unusually pure as gold goes. This is about 85% pure gold, but it can also be found like this. And this is a gold nugget that was found in a river, on a riverbed, and it's a heavy piece of gold. It's between about 1 and 1.5 ounces, which means that at today's prices it's worth about $2,000. And it's that inherent value that makes mines like this worth operating. Something a bit odd about the value we attach to gold. Throughout history, people have gone to extraordinary lengths to get their hands on this most precious substance, which is strange because it isn't particularly useful for anything.
Most of the gold that's been extracted throughout human history has ended up as jewellery, but it has got one thing going for it, and that's that it is incredibly rare.
The gold mined from the earth in all of human history would only just fill 3 Olympic-sized swimming pools. And it's that scarcity that makes gold valuable. But gold is just one of many rare elements.
There are over 60 elements heavier than iron in the universe. Some are valuable, like gold, silver, platinum. Some are vital for life, like copper and zinc, and some are just useful, like uranium, tin and lead. But across the universe there are vanishingly small amounts of those heavy elements.
The reason for that scarcity is that creating substantial amounts of the heaviest elements requires some of the rarest conditions in the universe. And we need to look far into space to find them. In a galaxy of 100 billion stars, these conditions will exist on average for less than a minute in every century. That's because they are only created in the final death throes of the very largest stars. Stars of at least 9 times the mass of our Sun. Only they can reach the extreme temperatures needed to create large amounts of the heavy elements. Deep in the heart of the star, the core finally succumbs to gravity. It falls in on itself with enormous speed. rebounds with colossal force. As the blast wave collides with the outer layers of the star, it generates the highest temperatures in the universe, 100 billion degrees. These conditions last for just 15 seconds, but it's enough to form the heaviest elements like gold. It's called a supernova, the most powerful explosion in the universe.
You know, it's quite a thought that something as precious to us as the gold in the wedding ring was actually forged in the death of a distant star millions of light years away, billions of years ago.
Despite the rarity of supernovae, when they do happen, they're the most dramatic events in the sky.
This is a picture of the Torrential Nebula, which is a cloud of gas and dust in the Large Magellanic Cloud, which is a satellite galaxy of the Milky Way. And this is what it looks like on any clear, starry night of the year. But on one night in 1987, the Torrential Nebula looked like that. You see that a new bright star has appeared in the sky. This is a supernova explosion, the explosive death of a massive star. And they're incredibly violent cosmic events, as this picture beautifully shows. This is a galaxy about 55 million light years away from Earth, but this is a supernova explosion in that galaxy. And you see that it's shining as brightly as the galactic core. There may be 1 billion suns in that core, and one supernova can shine as brightly as that.
Yet to really appreciate the scale of these explosions, we would need to see one up close, to see a star die in our own galaxy, the Milky Way. Although on average, there's one big supernova in each galaxy every century, there hasn't been one in the Milky Way since the birth of modern science. The last was in 1604, so we're long overdue. Astronomers are now searching the skies for the star that is most likely to go supernova. And amongst the leading candidates, there's a familiar name.
This is the constellation of Orion, and this is Betelgeuse. And we know it's extremely unstable because it's dimmed by about 15% in the last 10 years. Now, astronomers think that this star could go supernova at any moment. That could mean any time in the next million years, but equally, it could explode tomorrow. And Betelgeuse is only 600 light years away. Now when it goes, Betelgeuse will be incredibly bright. It'll be by far the brightest star in the sky. It may shine as brightly as a full moon. It will be almost a second sun in the daylight.
In this single instant, Betelgeuse will release more energy than our Sun will produce in its entire lifetime. As the star is torn apart, it will fire out into space all the elements that it created in its life and death. Those elements will spread out to become a nebula, a rich chemical cloud drifting through space. And at the heart of the nebula will be a tiny beacon of light, the remnant of a star once more than 1.5 billion kilometers across, that has been crushed out of all recognition by gravity. This is Betelgeuse, the neutron star. And it's how this once mighty star will end its life.
Now once Betelgeuse is gone, the constellation of Orion will look very different. I mean, there'll just be a hole in the sky where that brilliant bright red star once shone. But it's in the deaths of old stars that new stars are born. It's very much like the cycle of death and rebirth here on Earth, but played out on a cosmic scale. And you can see that happening today in the constellation of Orion, because in the sword handle you can see this, the Orion Nebula. Now it's nothing more than a misty patch of light in the night sky to the naked eye. But if you look more closely, you see that there is a lot more going on.
The Orion Nebula is one of the wonders of the universe. Hidden in its clouds are bright points of light. These are new stars forming from the elements blown out by supernova explosions. New stars being born from the remains of dead ones. And it's from this universal process of death and rebirth that we emerged. Because it was in a nebula just like this, 5 billion years ago, that our sun was formed. Around it, a network of planets formed. Among them was the Earth. Everything we find on the Earth today also originated in that nebula. But that is not the end of the story of how the universe created us. Because when we look deep into the nebula, we don't just see individual elements, we see greater complexity, the seeds of our own existence.
Well, this is a spectrum of the light from the Orion Nebula taken by the Herschel Space Telescope. So it really is a picture of light from interstellar space. You know, I wouldn't normally show you a graph like this, but this is fascinating because what it shows is that that gas cloud, the Orion Nebula, is not just a cloud of elements. There's complex chemistry here happening in deep space, because each peak on this graph corresponds to a different molecule. And there are some molecules present that I suppose are quite obvious. There's water, and there's sulfur dioxide. But there are also complex carbon compounds in here. So there's methanol, there's hydrogen cyanide, there's formaldehyde, there's dimethyl ether. So what we're seeing here is complex carbon chemistry happening in deep space.
That carbon chemistry is the beginning of the chemistry of life. And there is surprising evidence that this chemistry may have had a direct impact on the evolution of life on Earth. That evidence comes from meteorites. Debris left over from the formation of the solar system that occasionally collides with the Earth. One of the most productive places for finding meteorites is the Atacama Desert in the high Andes of South America. This is a meteorite, a piece of rock that fell to Earth from somewhere out there in the solar system, and it is certainly older than any rock you can see here. It's probably older than any rock you can find anywhere on Earth, because it formed from the primordial gas cloud, that nebula that collapsed to form the sun and the planets over 4.5 billion years ago. So it's incredibly ancient. Now this is a slice, a cross-section through a meteorite. You see those little brown areas in there? Well, in those brown areas we found amino acids, the building blocks of proteins, which are the building blocks of meat, the building blocks of life, incredibly complex carbon compounds. So this says that the complex carbon chemistry you need to send you on the path to life was happening out there in space 4.5 billion years ago. So the first amino acids on Earth, the fundamental building blocks of life, may have formed in the depths of space and been delivered to the Earth on meteorites. When we look out into space, we are looking into our own origins. Because we are truly children of the stars. And written into every atom and every molecule of our bodies is the entire history of the universe, from the Big Bang to the present day. Our story is the story of the universe. Every piece of everyone, of everything you love and everything you hate, of the thing you hold most precious, was assembled by the forces of nature in the first few minutes of the life of the universe, transformed in the hearts of stars, or created in their fiery deaths. And when you die, those pieces will be returned to the universe in the endless cycle of death and rebirth. What a wonderful thing it is to be a part of that universe. And what a story. What a majestic story. Why are we here? Where do we come from? These are the most enduring of questions, and it's an essential part of human nature to want to find the answers. Now we can trace our ancestry back hundreds of thousands of years to the dawn of humankind, but in reality our story extends far further back in time. Our story starts with the beginning of the universe. It began 13.7 billion years ago, and today it's filled with over 100 billion galaxies, each containing hundreds of billions of stars. In this series, I want to tell that story, because ultimately we are part of the universe, so its story is our story. The force at the heart of this story is gravity. This fundamental force of nature built everything we see. It creates shape and order, and it initiates patterns that repeat across the heavens. But gravity also forges some of the most alien worlds in the cosmos. Worlds that defy belief. The quest to understand this fundamental force of nature has unleashed a golden age of creativity, exploration and discovery. And it's led to a far deeper understanding of our place in the universe. every moment of our lives, we experience a force that we can't see or touch. Yet this force is able to keep us firmly rooted to the ground. It is, of course, gravity. But despite its intangible nature, we always know it's with us.
I managed to ask you, how do you know that there's gravity around here? And you might say, well, it's obvious, you know, I can just do an experiment, I can drop something. Well, yes, but actually, gravity is a little bit more subtle than that. But to really experience it, to understand it, you have to do something pretty extreme.
And this plane has been modified to help me do it. Thanks to its flight plan, it's known as the Vomit Comet. Once we climb to 15,000 meters, this plane does something no ordinary flight would do. Its engines are throttled back and the jet falls to Earth. And then, something quite amazing happens. By simply falling at the same rate as the plane, for a few fleeting moments, we are all free of gravity's grip. But this isn't just a joyride.
Now look, there's something very profound here, because although I'm falling towards the ground, as you see, gravity has completely gone away. Gravity is not here anymore. I've cancelled gravity out just by falling. Can you understand that? Then you will understand gravity.
So it is possible, by the simple act of falling, to get a very different experience of gravity. But this force of nature does more than just bring us back down to Earth. Gravity also plays a role on the grandest of stages, because across the universe, from the smallest mote of dust to the most massive star, gravity is the great sculptor that created order out of chaos. Since the beginning of time, gravity has been at work in our universe. From the primordial cloud of gas and cosmic dust, gravity forged the stars. It sculpted the planets and moons and set them in orbit around the newly formed suns. And gravity connects these star systems together in vast galaxies and steers them on their journey through unbounded space. Over the centuries, our quest to understand gravity has allowed us to explain some of the true wonders of the universe. But at a deeper level, that quest has also allowed us to ask questions about the origin and evolution of the universe itself. To understand how gravity works across the universe, we need look no further than the ground beneath our feet.
Well, the first scientist to really think about it was Isaac Newton back in the 1680s. And he said this: gravity is a force of attraction between all objects. Now, the force of attraction between these two rocks is obviously very small, almost impossible to measure. And that's because the force is proportional to the masses of the objects. And these things are not very massive. But there is a more massive rock around here. So what I'm standing on, planet Earth.
The mass of our Earth generates a gravitational pull strong enough to sculpt the entire surface of the planet. It causes water to gouge out vast canyons. It sets the limit for how high mountains can soar, and it shapes whole continents. But this invisible force does more than just shape our world. The skies are always changing. The constellations rise and fall in different places every night, and the planets wander across the background of the fixed stars. But throughout human history, there's been one constant up there in the night sky, because every human that's ever lived has gazed up at the moon and seen one face shining back at us. The reason why we never see the dark side of the moon is all down to the subtlety with which gravity operates. Millions of years ago, the moon rotated rapidly, but from the moment it was born, our companion felt the tug of gravity. Just as the moon creates great tides in our oceans, the Earth caused a vast tide to sweep across the surface of the moon. But this tide wasn't in water, it was in rock. Imagine that this is the moon, and over there is the Earth. The Earth's gravity acts on the moon and stretches it out into a kind of rugby ball shape. Now, the size of that tidal bulge facing the Earth is something like 7 meters in rock. And then as the moon rotates, that bulge sweeps across the lunar surface. And imagine what that would look like here. You'd see a tidal wave sweep across this landscape with the rock rising and falling by 7 meters. This massive wave acted like a brake and gradually slowed the moon down. Eventually, the tidal bulge became aligned with the Earth, locking the speed of the moon's rotation. So the time it takes the moon to spin once is almost the same as the time it takes to orbit the Earth. So there is no dark side of the moon, just a side that gravity hides from our view. The bond that gravity creates between the Earth and the Moon is repeated across the cosmos. It's the glue that holds the planets in orbit around the Sun. And it binds our solar system and countless other solar systems together to form galaxies like our own Milky Way. But gravity's influence can be felt even further, because it controls the fate of galaxies. When you look up into the night sky, then you see the universe as it looks in visible light, with the glowing of the stars and the galaxies. But that's only part of the story, because the universe is full of dust and gas, which you can't see with a conventional telescope, but you can see with a telescope like this. Radio telescopes, like the Very Large Array in New Mexico, are able to peer deep into space and reveal the incredible attractive power of gravity. This is Andromeda, a spiral galaxy roughly the same size and mass as the Milky Way. This island of over 1 trillion stars sits over 2.5 million light years away, but every hour that gap shrinks by 500,000 kilometres. Whilst most galaxies have been rushing away from each other ever since they formed just after the Big Bang, some galaxies form so close together that they're locked in a gravitational embrace. Now, the Milky Way and Andromeda are two such galaxies, and computer simulations suggest that they will collide together in around 3 billion years' time. And look at that. That's a simulation of the Milky Way galaxy and the Andromeda galaxy colliding together. And all these wisps of smoke getting thrown out are stars. And these are star systems getting ripped out of the galaxy and thrown off into interstellar space. These two islands of hundreds of billions of suns have flown through each other, and gravity has exerted its grasp and dragged them back again. And just remember that we are one of those dots. You know, our sun and the Earth and the solar system are either going to be flung out into interstellar space, or they're going to be in here in this maelstrom of hundreds of billions of suns swirling around each other and forming the core of a new galaxy. But just imagine what it would be like to gaze up at the sky as Andromeda approached. And the sky would be ablaze with the light of hundreds of billions of suns, and the imminent collision would provide the energy to generate the births of hundreds of millions more. And what a magnificent sight it would be. But far more magnificent is the immense scale of gravity's embrace. It holds galaxies together across hundreds of billions of kilometres, and in doing so, it creates the most magnificent structures. Our own Milky Way is part of one of these, the Virgo cluster. Every point of light in this image is not a star, but a galaxy. There are 2,000 galaxies in this cluster, and they are all bound together by gravity, making it the largest structure in our intergalactic neighbourhood. There seems to be no limit to the reach or power of gravity. Its influence can be felt across the vast expanses of space and time. But there's something very interesting about gravity, because it is by far the weakest force of nature. You look, I can pick this rock up off the ground, even though there's an entire planet Earth, trying to pull it down. So, if gravity is so weak, how come it's so influential? Gravity may be weak here on Earth, but it's not so weak across the cosmos. This invisible force varies on all the planets in the solar system and on the exoplanets we've discovered orbiting other suns. To experience what gravity feels like on these worlds, I need to go for a spin.
This is a centrifuge. It was built in the 1950s to test whether fighter pilots had the right stuff, but it's going to allow me to feel what it'd be like to stand on the surface of any of the planets in the solar system that are more massive than the Earth. And in fact, also what it'd be like to stand on some of the planets that we've found around distant stars.
Right, I'll have to strap you in first of all. Let me see, hold up. This is a go-and-go switch. It's an emergency switch in case something happens and you release it, centrifuge will stop.
I was just told by the F-16 fighter pilot who's just been in here that it's 100 times more uncomfortable than being in a jet fighter. But I was kept confident because I've been in jet fighters and didn't find it too uncomfortable, but apparently this is 100 times worse.
Doors closed again, problems there, symptoms are there, doctor is ready. We'll start up the centrifuge, Brian, and bring you in orbit, and it happens in 3, 2, for now.
The first planet I'm travelling to is Neptune. Its gravity is just fractionally stronger than here on Earth.
So this is the gravitational field on Neptune, and you feel, you know what, I could probably get used to this. I could probably live on the surface of Neptune.
Can you lift your hands a little?
There we go.
Yeah, and down.
And it is actually quite an effort. It is noticeably heavier. It's like having a reasonably heavy weight in your hand.
You're ready to go to 2.5 G?
Yes, and then we'll move from Neptune to Jupiter.
Let's go there.
Jupiter is over 1,300 times more massive than the Earth, but because it's mostly gas, it's not very dense, so its gravity is just over twice as strong at its surface.
Well, now actually it is quite difficult to lift my hand, and that's 2.5 G. I wouldn't want to sit here for half an hour.
And can you lift both of your hands above your head and see what happens there?
Let's see, so actually, just about, but actually it's an immense amount of hard work. But it would be hard work living on Jupiter.
Let's go to 4G.
Actually, this is heading to a planet around a planet called Ogle 2 TR-L9b, which is around a star in the constellation of Carina. It's one of the exoplanets we've discovered. Oh, and there we go. Now that is actually beginning to feel quite unpleasant.
Can you describe what you're feeling?
A very heavy face.
Alright.
My head is extremely heavy.
How about your lungs? Inhaling, exhaling, breathing?
It's much harder work. I can't lift my hand off my leg.
Okay.
And that's at 4G.
Yeah.
But my head and my face feel very, very heavy.
Yeah.
It's quite an unpleasant feeling.
We'll go to 5 and let me know if you have any visual disturbances.
I'm now en route to a newly discovered exoplanet, WASP-8b.
4.4.
This world sits in the small and faint constellation of Sculptor.
Quite hard to speak.
It has a gravitational force nearly 5 times that of the Earth.
Alright, we'll go to 5G.
Oh, very foggy.
Okay.
Very foggy.
Very foggy. Still foggy?
Yeah.
Alright.
Take it down.
Okay, we'll take it down.
Very interesting.
It was, wasn't it?
My face felt a bit saggy there.
Oh, you looked a little different.
It was quite unpleasant that time actually. So it went very quickly up to 5G. And what happens is, well for me anyway, is vision becomes very, very foggy. Just the whole thing just blurs and blurs and blurs. So you realise that we're obviously very finely tuned to live on a planet that has an accelerator-induced gravity of 1G. When you go to 2G, it's difficult. When you go to 3G and 4G, it becomes unpleasant. And 5G, anyway, for me, was on the border of being so unpleasant that you pass out. So although gravity feels weak here on Earth, it certainly isn't weak everywhere across the universe. And that's because gravity is an additive force. It scales with mass, so the more massive the planet or star, the stronger its gravity. The body with the strongest gravity in our solar system is the Sun. Our star has so much mass packed inside a relatively small space that it has a gravitational pull at its surface 28 times that of the Earth. If I were able to set foot on this world, all the blood would be pulled out of my upper body, and I would die in less than a minute. But our Sun's gravitational force is nothing compared to the extreme G found at the surface of one of the strangest places in the universe. Imagine the gravity on a world with more mass than our Sun, crammed into a sphere just 20 kilometres across. We first detected such a wonder just 40 years ago, but the story of its discovery begins over 1,000 years earlier. This is Chaco Canyon in New Mexico in the southwestern United States, and it was home to what's become known as the Chacoan civilization. Well, this is Pueblo Bonito, one of the so-called Chacoan Great Houses. And back in the 1100s, this place had over 600 rooms. It's thought that this building must have been ceremonial or religious, a cathedral, if you like. The Chacoan Great Houses are aligned with interesting objects in the sky, so the points at which the sun and moon rise at important times of the year. So it seems that by constructing these
grand buildings, the Chacoans were not only trying to place themselves at the heart of local culture, but also to place themselves at the heart of the cosmos. Very little is known about the Chacoan culture because no written text has ever been discovered. But in another part of the canyon, there is a record of a spectacular event that they witnessed in the sky in 1054. I've known about this place since I was about 12 or 13 years old, and the reason is this book and the television series Cosmos, Carl Sagan's masterpiece, probably the most important reason that I got interested in astronomy. On page 232, there's a picture that's always fascinated me and captured my imagination, and it's a photograph of that wall of rock, and in particular a painting that's on the overhang, because it's thought that that painting is a record of one of the most spectacular and magical events in the cosmos. On July 4th, 1054 AD, a bright new star appeared, and it outshone every other star in the night sky for over 3 weeks. It was so bright that it was visible in the daytime. And it's thought that this painting is the Chacoan people's record of that astronomical event. Now the reason we think that is that using modern computer techniques, you can wind back the night sky and say, where would the moon have been? Where would the stars have been? And you find that in that direction, the moon would have risen and tracked across the night sky, and the new star would have been very, very close to the crescent moon. We now know that that new star was in fact the explosive death of an old star, a supernova explosion, a star literally blowing itself apart at the end of its life. Throughout a star's life, there is a constant battle between energy pushing out and gravity pushing in. As long as the star burns, the two forces balance each other out. But when it runs out of fuel, gravity wins, and the star collapses and then explodes with the brightness of 1 billion suns. We can no longer see the supernova the Chacoans saw, but we can still marvel at what it left behind. This is the Crab Nebula, the remains of that exploding star that the Chacoans saw in these skies 1,000 years ago. It's an expanding cloud of gas and dust, the remains of that dying star. And the colours are different chemical elements. So the orange is hydrogen, the red is nitrogen, and those filaments of green are oxygen. While the explosion blew most of the stellar material out into the cosmos to form this vast nebula, we now know that this wasn't the end of the story. At the centre of the nebula lies the remnant of the star, its core crushed by the force of gravity. That is a neutron star, an image taken by the Chandra X-ray satellite. The central blob there is only about 20 kilometres across, but it's got the mass of our sun, a star the size of a city. It's spinning at a rate of over 30 times a second, 1,800 revolutions per minute. And it really is an astonishingly alien world. As the neutron star spins, jets of particles stream out from the poles at almost the speed of light. These jets are powerful beams that sweep around as the star rotates. When the beams sweep across the Earth, they can be heard as regular pulses, so we call them pulsars. But it's not this rhythmic noise that makes the crab pulsar a wonder. It's the extraordinary nature of gravity on this alien world. If I were to be on its surface, then the gravitational pull on me would be 100,000 million times that I feel on Earth. And that means that if I were to jump from the top of that projection screen, and by the time I hit the ground, I'd be travelling at over 4 million miles an hour. That's a lot of gravity. Pulsars have such extreme gravity because they're made of incredibly dense matter. To understand why, we have to look at what gravity can do to matter at the very smallest scales. Everything in the universe is made of atoms, and until the turn of the 20th century it was thought that they were the smallest building blocks of matter. I mean, the word itself comes from the Greek atomos, which means indivisible. But we now know that atoms are made of much smaller stuff. Atoms consist of an atomic nucleus surrounded by a cloud of electrons. And whilst almost all of the mass is contained in the nucleus, it is incredibly tiny compared to the size of an atom. And if this were a nucleus, then the cloud of electrons would stretch out to something like 1 kilometre away. I mean, that's from here to that rock. And electrons on this scale are incredibly tiny. They're just like specks of dust, and there aren't many of them. So imagine a giant sphere centred on the atomic nucleus, stretching out all the way to that rock and beyond, with just a few points of dust in it. That's an atom. So that means that matter is almost entirely empty space. I'm full of empty space. The Earth is full of empty space. Everything you can see in the universe is pretty much just empty space. So if everything in the universe is made up of atoms, and atoms are 99.9999% empty space, then most of the universe is empty. But in the crab pulsar, the force of gravity is so extreme that the empty space inside the atoms is squashed out of existence. So all you're left with is incredibly dense matter. Imagine this was matter taken from a neutron star, then it would weigh more than Mount Everest. Or, to put it another way, if I took every human being on the planet and squashed them so they were as dense as neutron star matter, then we would all fit inside that. And if I were to drop my neutron star stuff to the ground, then it would slice straight through the Earth like a knife through butter. Wherever we look in the universe, we see gravity at work. It creates shape and structure. It governs the orbits of every planet, star and galaxy in ways we thought we were able to predict. But there was a flaw in our understanding of this force, and it was exposed by one of our close neighbours. This is Mercury. For thousands of years we've marvelled as this fleet-footed planet races across the face of the sun. But 150 years ago, astronomers noticed something strange about Mercury's orbit.
Imagine that this rock is the sun and this is Mercury. Now Mercury has quite a complex orbit. For one thing, it's not a perfect circle, it's quite an elongated ellipse. So at its closest approach to the sun, it's around 46 million kilometres away, and then it drifts out to something just under 70 million kilometres. But you can calculate Mercury's orbit very precisely using only Newton's laws of gravity. So astronomers used to predict the exact time when you could look up into the sky, look at the sun, and see the tiny disk of Mercury pass across its face. But the thing was, they never got it right. They predicted it time and time again, and every time it happened, they got it slightly wrong, which was an immense embarrassment. So what they did was that rather than question Newton, they invented another planet, and they called it Vulcan. And they said that there must be another planet somewhere in the solar system which is always invisible from Earth, but which is embarrassment. So what they did was that rather than question Newton, turned Mercury's orbit a bit, and so that was the reason their calculations were wrong.
For decades, astronomers searched and searched for Vulcan. But they never found it, because Vulcan didn't exist.
The explanation, the real explanation, was even more interesting than inventing the planet Vulcan, because it required a modification, in fact, a complete rewriting of Newton's law of gravity.
Gravity is not a force pulling us towards the centre of the Earth like a giant magnet. In a sense, gravity isn't really a force at all. Describing the nature of gravity turned out to be one of the great intellectual challenges. But almost 200 years after Newton's death, a new theory emerged.
The new theory, called general relativity, was published in 1915 by Albert Einstein after 10 years of work, and it stands to this day as one of the great achievements in the history of physics. See, not only was it able to explain with absolute precision the strange behaviour of Mercury, but it explains to this day everything we can see out there in the universe that has anything to do with gravity. And, most importantly of all, it explains how gravity actually works.
Gravity is the effect that the stars, planets and galaxies have on the very space that surrounds them. According to Einstein, space is not just an empty stage, it's a fabric called space-time. This fabric can be warped, bent and curved by the enormous mass of the planets, stars and galaxies.
You see, all matter in the universe bends. The very fabric of the universe itself. Matter bends space. I bend space. These mountains bend space, but by the tiniest of amounts. But when you get onto the scale of planets and stars and galaxies,
then they bend and curve the fabric of the universe by a very large amount indeed.
And here is the key idea. Everything moves in straight lines over the curved landscape of space-time. So what we see as a planet's orbit is simply the planet falling into the curved space-time created by the huge mass of a star. This is able to explain Mercury's erratic orbit. Because of the planet's proximity to our Sun, the effects of the curvature of space-time matter far more for Mercury than for any other planet in the solar system.
But this idea of curved space is difficult to imagine, but you can only step outside of it. We can only float above space-time and look down on it. This is what our universe would look like.
You would see the mountains and valleys. You would see the little peaks and troughs created by planets and moons, and you would see these vast, deep valleys created by the galaxies. And you would see planets and moons and stars circling the peaks as they follow their straight line paths through the curved landscape of space-time. So one way to think about gravity is that everything in the universe is just falling through space-time.
The moon is falling into the valley created by the mass of the Earth. The Earth is falling into the valley created by the Sun, and the solar system is falling into the valley in space-time created by our galaxy. And our galaxy is falling towards other galaxies in the universe.
Einstein's theory of general relativity is so profound, so beautiful, that it can describe the structure and shape of the universe itself. But remarkably, the theory can also predict its own demise, because it predicts the existence of objects so dense, so powerful, that they warp and stretch and bend the structure of space-time so much that they can stop time, and that they can swallow light. These are objects so powerful that they can tear all the other wonders of the universe apart. Since the dawn of civilization, we've peered at the stars in the night sky and tracked the movements of the planets. We see these familiar patterns repeated across the whole universe. But when we train our telescopes to the stars that orbit around the centre of our galaxy, we see something very unusual.
Well, this is one of the most fascinating and important movies made in astronomy over the last 10 or 20 years. This is real data. Every point of light in this movie is a star orbiting around the centre of our galaxy. They're known as the S-stars. Our
Our sun takes around 200 million years to make its way around the Milky Way. One of these S stars takes only 15 years to go around the centre of the galaxy. It's travelling at 3,000 or 4,000 kilometres per second. Now, by tracking the orbits, it's possible to work out the mass of the thing at the centre. The answer took astronomers by surprise, I think it's fair to say, because the object in the centre of our galaxy is 4 million times as massive as the Sun, and it fits into a space smaller than our solar system. Now, there's only one thing that anyone knows of that can be so small and yet so massive, and that's a black hole. So what we're looking at here is stars swarming like bees around a supermassive black hole at the centre of the Milky Way galaxy. We think black holes can be smaller than an atom or 1 billion times more massive than our Sun. Some are born when a star dies. When a star around 15 times the mass of our Sun collapses. All the matter in its core is crushed into an infinite void of blackness known as a stellar mass black hole. Black holes are the most extreme example of warped space-time. They have such enormous mass crammed into such a tiny space that they curve space-time more than any other object in the universe. The immense gravitational pull of these monsters can rip a star apart. They tear matter from its surface and drag it into orbit. This superheated matter spins around the mouth of the black hole, and great jets of radiation fire from the core. Although these jets can be seen across the cosmos, the core itself remains a mystery. Black holes curve space-time so much that nothing, not even light, can escape, so their interior is forever hidden from us. But because we understand how matter curves the fabric of space, it is possible to picture what is happening. Near a black hole, space and time do some very strange things, because black holes are probably the most violent places we know of in the universe. This river provides a beautiful analogy for what happens to space and time as you get closer and closer to the black hole. Now, upstream the water is flowing pretty slowly. Let's imagine that it's flowing at 3 kilometers per hour and I can swim at 4. So I can swim faster than the flow and can easily escape. But
as you go further and further downstream towards the waterfall in the distance, the river flows faster and faster. Imagine I was to decide to jump into the river just there on the edge of the falls. The water is flowing far faster than I could swim. So no matter what I did, no matter how hard I tried, I would not be able to swim back upstream. I would be carried inexorably towards the edge and I would vanish over the falls. Same close to a black hole, because space flows faster and faster and faster towards the black hole. Literally, this stuff, my space that I'm in, flowing over the edge into the black hole. And at a very special point called the event horizon, space is flowing at the speed of light into the black hole. Light itself, travelling at 300,000 kilometres per second, is not going fast enough to escape the flow, and light itself will plunge into the black hole. Well, as you fall into a black hole across the event horizon, then if you were going feet first, your feet would be accelerating faster than your head. So you would be stretched, and you would be quite literally spaghettified. Now as you get right to the centre, then our understanding of the laws of physics breaks down. Our best theory of space and time, Einstein's theory of general relativity, says that space and time become infinitely curved, that the centre of the whole becomes infinitely dense. That place is called the singularity, and it is the place where our understanding of the universe stops. Gravity is the great creator, the constructor of worlds. That's because it's the only force in the universe that can reach out across the vast expanses of space and pull matter together to make the planets, the moons, the stars, and the galaxies. But gravity is also the destroyer, because it's relentless, and for the most massive objects in the universe, for the most enormous stars and the centres of galaxies, gravity will eventually crush matter out of existence. Now the word beautiful is probably overused in physics. I probably overuse it. But I don't think there is any scientist who would disagree with its use in the context of Einstein's theory of gravity. Because here is a theory that describes a universe that is bent and curved out of shape by every moon, every star, and every galaxy in the sky. And everything in the universe has to follow those curves, from the most massive black hole to the smallest mote of dust, even to beams of light. But the most tantalising thing about Einstein's theory of gravity is we know that it's not complete.
We know that it's not the ultimate description of the structure and shape of the universe. And that, for a scientist, is the most beautiful place to be, on the border between the known and the unknown. That is the true wonder of the universe. There's so much more left of it to explore. Why are we here? Where do we come from? These are the most enduring of questions, and it's an essential part of human nature to want to find the answers. Now we can trace our ancestry back hundreds of thousands of years to the dawn of humankind, but in reality our story extends far further back in time. Our story starts at the beginning of the universe. It began 13.7 billion years ago. And today it's filled with over 100 billion galaxies, each containing hundreds of billions of stars. In this series, I want to tell that story because ultimately we are part of the universe. So its story is our story. It's a story that we wouldn't be able to tell were it not for the one thing that connects us vividly to our vast cosmos: light. Light reveals the wonders of the universe in all their glory. Stars that shine with the light of 1,000 suns and vast swirling galaxies. But light is also a messenger from a long forgotten era, and contained in the light from these faraway places is the story of our universe's origin and evolution. Through light we can stare back across the entire history of the universe and discover how it all began, and ultimately see how light breathed life into us. This is Karnak Temple in Egypt. Built by the ancient pharaohs, this vast complex was erected to honour Amun-Ra, god of all gods, god of the sun. This worship reaches its peak during one fleeting moment in the solar calendar. An event so brief it lasts for little more than a minute. This temple is built to align with an astronomical event that happens just once a year, the sunrise at the winter solstice. The solstice is Latin for sun stands still, because as the Earth orbits around the sun and the year passes, the point at which the sun rises above the eastern horizon moves. So here in Egypt, in summer, the sun rises over in that direction, and then as summer turns to autumn, turns to winter, the sunrise point drifts along until today, on December 21st, at 6:30 AM, in midwinter, the sun rises exactly between the pillars of this temple. Once a year for over 3,000 years, the sun has risen between the two pillars and cast its light into the temple. There it is, with the light from our star cascading down this magnificent structure. Then you can literally feel the history of this place. It's easy to forget that this is 3,500 years old. So, in 1500 BC, the most powerful man on the planet, the Pharaoh of Egypt, would have stood here on December 21st every year just to greet and experience the light from Amun-Ra. This moment that the Egyptians worshipped instinctively, we now understand in exquisite detail. As the Earth journeys through the solar system, it's bathed in the light of the star that sits at its centre. This light has travelled some 150 million kilometres from the surface of the sun. And at the winter solstice, that light pours into the temple at Karnak. Well, this building is honestly the most magnificent structure I've ever seen. But it's not built on the scale of men, it's built on the scale of gods, of one god, Amun-Ra, the god of the sun. As the sun sinks below the horizon, the night falls, the whole universe of suns fades into view. We no longer build temples to our sun. We build machines that allow us to peer deeper into space than ever before, to far distant suns out there in the galaxy and beyond. On a night like this, there are about 2,500 stars visible to the naked eye. But when we started building telescopes instead of temples, we discovered that there are billions more. Every star we see in the night sky is a sun that sits within our own galaxy, the Milky Way. As we step away, our sun gradually fades to become just one dot in a sea of stars. We now know that we are about halfway out from the centre of this beautiful cosmic structure. But even though these worlds are many millions of kilometres away, we know them intimately by their light. These waves of light are messengers from across the cosmos, and through them we have discovered the wonders of our galaxy. This is the Lagoon Nebula. From a distance, this cloud of dust and gas appears beautiful and serene. But this is a furnace where new stars are forged. The Lagoon Nebula sits about 5,000 light years from Earth, but it can still be seen with the naked eye because it's 100 light years across and brightly lit by the hot, young new star that sits at its centre. A giant called Herschel 36. This newly born star is over 20 times more massive than our Sun and burns much hotter, which makes the light that pours from its surface blue. And there are even bigger stars in our galaxy. 7,500 light years from Earth is a star that dwarfs even Herschel 36. Its name is Beta Carinae. This monster star is over 100 times more massive than our Sun and burns about 4 million times brighter, making it one of the most luminous stars in the Milky Way. All we know about these incredible worlds has been brought to us on wave after wave of light. Our galaxy is a symphony in light. The Milky Way is home to 200 billion stars. But our galaxy is just the beginning. For each of these stars, there are a billion more in the universe beyond. Across the unimaginable reaches of space, light has allowed us to journey to the most distant galaxies, to see the births and deaths of stars. No matter how far we follow the light, no matter how many billions of miles we cross, the nature of light itself allows us to go on a much richer journey, because to look up and to look out is to look back in time. See, those ancient beams of light are messengers from the distant past, and they carry with them a story, the story of the origin of the universe. In order to read this story, to see how light can transport us to the past, we must first understand one of its fundamental properties, its speed. Everything in our universe has a speed limit. Even intangible phenomena, like waves of sound and light. These speed limits are very real physical barriers, and they have profound consequences for our understanding of the universe. Today, I'm going to try and break one of those barriers. This is a Hawker Hunter. It was built in the 1950s, when breaking the sound barrier was at the very limit of our technical abilities. A sound barrier is an incredibly evocative term, it has an almost legendary status in the history of aviation. But there's nothing fundamental about it. It's something that you can overcome with some extremely clever engineering and, in the early days, quite a lot of courage. The reason we don't usually think about sound as having some kind of speed limit, a limit in speed, is because it is incredibly fast compared to the things we're used to in everyday life. But today, we're going to try and break it. I'm going to try and break it, sat in this marvellous machine. On Earth, the speed of sound, depending on altitude, is around 1,200 kilometres per hour, known as Mach 1. This jet isn't designed to fly that fast in normal flight, but there is a way to make it travel faster than sound, and for that, we need to fly high. As the plane flies faster, it begins to catch up with its own sound. The sound waves simply can't get out of the way fast enough, so they begin to pile up at the front of the jet. But to outrun our sound waves, we need to push this jet to its absolute limit. In just seconds, the jet smashes through the sound barrier. This can be heard from the ground as a sonic boom.
It was a doddle, actually. Well, you know, having said that, it was inverted full throttle at 42,000 feet, but it's a different definition of doddle. So this magnificent piece of engineering is fast enough, if you just push it a little bit, to outrun its own sound. So the sound barrier is negotiable. You can smash your way through it. But the speed of light, the light barrier, well, that's a very different story. Sound has a definite speed that we can measure. For years, worlds with mind thought that light was different, that it travelled instantaneously from object to eye. Then, around 350 years ago, the truth about light was revealed through a combination of one man's genius and the clockwork orbits of the heavens. Ever since Galileo discovered that Jupiter had moons, astronomers realised that you could use Jupiter and its moons as a very precise clock in the sky. So here's the solar system, there's the Sun, there's the Earth, here's Jupiter, and here is Jupiter's innermost moon Io. Now it was known that Io takes precisely 42.5 hours to orbit around Jupiter. So if, from the Earth, you see Io emerge from behind Jupiter at, say, midnight on a Tuesday, then you know that it should re-emerge again at 6:30 on Thursday afternoon. Beautiful. Now one of the men charged with making precise tables of exactly when Io should be seen to emerge from behind Jupiter was the Danish astronomer Ole Rømer. But he noticed something surprising. See, depending on the time of year, Io emerged later than expected or earlier than expected. Now Rømer's genius was to realise that had nothing to do at all with the orbit of Io around Jupiter. It was to do with the orbit of the Earth around the Sun. See, what Rømer noticed was that when the Earth was in a position in its orbit so that it was close to Jupiter, then Io emerged earlier than it was expected to. Then, as the year passed and Earth moved around the Sun and got further away from Jupiter, Rømer noticed that Io then emerged later than it was expected to. And Rømer realised that it takes time for light to travel
from Jupiter to the Earth. So when the Earth is far away from Jupiter, it takes longer for the light to travel, and therefore you see Io emerge from behind Jupiter later than you would expect. Then, when the distance is small, it takes less time for the light to travel, and you see Io emerge earlier than you might expect. So Römer had discovered that light doesn't travel instantaneously. It moves through space with a finite speed. This remarkable insight led to a measurement of the speed of light. We now know that light travels at precisely 299,792,458 metres per second. That means that in the time it takes for me to click my fingers, light has travelled around the Earth 7 times, or that it travels 10 million kilometres in 1 year. And that's the yardstick we use to measure the universe, because 10 million kilometres is approximately 1 light year. The speed of light is the speed limit of the universe, built into the very fabric of space and time itself. But because light travels at a finite speed, a light year isn't just a measure of distance, it's also a measure of time. The further away an object is, the further back in time we see it. Now the distances that light travels on Earth are relatively short, so the time it takes light to travel to our eye is imperceptible. But when we look out to space, over astronomical distances, to the stars, planets and galaxies beyond, then light's finite speed has profound consequences. This is Tanzania in Eastern Africa, the cradle of humankind. It's here that some of our earliest ancestors walked 2.5 million years ago. And our evolutionary journey from the distant past to the present day ran in parallel with the journey of the light from the stars. The Sun is 150 million kilometres away. Now that's very close by cosmic standards, but light travels at only 300,000 kilometres per second. So that means that we're seeing the Sun as it was in the past, actually 8 minutes in the past. But when we look beyond our Sun to far more distant stars, we reach further back in time, across the whole of human evolution. And the deeper into space we look, the further back in time we see. As the Sun dips below the horizon and night falls, the universe just fades into view. And at first you see the bright planets. I can see Venus over there. And then the stars appear one by one, thousands of them shining in the sky. And then, as it gets darker and darker, the Milky Way appears, a vast swathe of billions and billions of suns as you look out towards the centre of our Milky Way galaxy. But I think, for me, the most magical thing you can see in the sky with the naked eye is just below the constellation Cassiopeia, the W of stars in the sky. I've got to say, that's amazing. Well, see, that misty patch of light is not a cloud in the sky. It's not even gas and dust in our galaxy. That is another galaxy. It's the Andromeda galaxy, which is roughly the same size as our own, an island of hundreds of billions of stars, 25 million kilometres in that direction. Like the Milky Way, Andromeda is a spiral galaxy. 2 ringed arms circling a light-filled centre. The core of Andromeda is packed with millions of old red stars. Very few new stars are born here. In contrast, its spiral arms shine with the light from clusters of hot, young blue stars. The light that pours from this stellar city connects us to a remarkable time in the story of human evolution. The light that I've just captured in my camera began its journey 2.5 million years ago. At that time, on Earth, there were no humans. Homo habilis, our distant ancestors, were roaming the plains of Africa. And as those light rays travelled through the vastness of space, our species evolved, and thousands and thousands and thousands of generations of humans lived and died. And then, 2.5 million years after their journey began, these messengers from the depths of space and from way back in our past arrived here on Earth, and I just captured them and took that picture. Light's finite speed opens a window onto the past and shows us Andromeda as it looked when our early ancestors walked the Earth 2.5 million years ago. But by peering further than the naked eye will allow, we can journey to a time way before human history, so far back that we can read the entire history of the universe. In the last 20 years, powerful space telescopes have carried us ever deeper into space, and we have become virtual time travellers. This is Centaurus A, one of our nearest neighbouring galaxies, only 10 million light years away. That means that the light began its journey from these old red and young white blue stars only 10 million years ago. And stepping out a little further, just to 14 million light years, there's this beautiful barred spiral galaxy, and again you can see just lanes and lanes of bright young blue stars, and this blue light has taken 14 million years to journey across the universe to my eye. This is NGC 520. And it's the product of a cosmic collision. But this galaxy is 100 million light years away. That means that the light began its journey from this galaxy to my eye when the dinosaurs roamed the Earth. Now, I think it's a beautiful thought that by capturing this faint light and rebuilding these spectacular images, We are, in a very real sense, connected to these galaxies, no matter how far away they are across the universe, connected by the light that's journeyed billions of years to reach us. But these spectacular galaxies are not the end of our journey into the past. In 2004, we peered further back in time than ever before and captured the light from the most distant galaxies in the universe. The image is called the Hubble Ultra Deep Field. It's a picture taken by the Hubble Space Telescope over a period of 11 days, and it focused its camera on the tiniest piece of sky just below the constellation of Orion. Now, it's a piece of sky that you would cover if you took your thumb, held it in front of your face, and then moved it 20 times further away. But the Hubble captured the faintest light from the most distant regions of the universe, and it took this photograph. Now, almost every point of light in that image is not a star, but a galaxy of over 100 billion stars. The most distant galaxies in that image are over 13 billion light years away. That means that the faint light from those galaxies began its journey to Earth 13 billion years ago. That's over 3 times the age of the Earth. Hubble allows us to peer back almost to the beginning of time itself. And out here, in deep space, it reveals a clue to how our universe began. When the Space Telescope stared across the cosmos, it saw galaxies glow in all different colours. But when it peered to the very edge of the visible universe, it captured these images and saw that every galaxy glowed red. Written in the red light from these distant worlds is the story of our universe's origin and evolution. To reveal it, we must explore one of the most beautiful qualities of light. For centuries, people thought that light just illuminated our world, allowed us to see, and nothing more than that. But we've since learned that there is a vast amount of information and detail contained within every beam of light. And that information is written in colour, to reveal how colour can unlock the secrets of our universe's creation and come to one of the most spectacular natural wonders on Earth. This is Victoria Falls in Zambia. This waterfall stretches for almost 2 kilometres, making it the largest curtain of falling water in the world. But I'm not here to marvel at the scale of this wonder. I've come to see a much more delicate feature that appears above the water. These magnificent rainbows are a permanent feature of the skies above Victoria Falls. Now, rainbows are a beautiful phenomenon, but I think that they're even more beautiful when you understand how they're made, because they are a visual representation of the fact that light is made up of, well, all the colours of the rainbow. Rays of light from the sun bend as they enter the water droplets. The light beams then reflect off the back of the droplets, and are bent for a second time as they leave. This bending and reflecting splits the light, and the colours hidden inside the white sunlight are revealed. But colour can tell us much more, because understanding the reddening of the galaxies has given us a profound insight into the nature of the universe.
What we see as different colours are actually different wavelengths of light. So blue light has a relatively short wavelength, and then you go through green and yellow all the way to the red end of the spectrum, which has a very large wavelength.
Starlight is made up of countless different wavelengths, all the colours of the rainbow.
When light is emitted by a distant star or galaxy, its wavelength doesn't have to stay fixed. It can be squashed or stretched. And when light's stretched, its wavelength increases and it moves to the red end of the spectrum. So the interpretation of the fact that the most distant galaxies appear red is that the space in between them and us has stretched during the time it's taken the light to journey over that vast distance. That means that our entire universe is expanding. Now just think about what an expanding universe implies, because if the galaxies are all rushing away from each other, that means that if you rewind time, then they must have been closer together in the past. And actually, if you just keep rewinding, then you find that at some point in the past, all the galaxies we can see in the sky were quite literally on top of each other. The universe was squashed down to a point. That implies that the universe may have had a beginning. And that is the Big Bang Theory.
Well, that's probably many people's picture of the Big Bang, this vast explosion that flung matter out into the void. But that's completely wrong. As we understand it at the moment, all of space was created at that moment. So the Big Bang didn't just happen somewhere out over there in the universe, it happened everywhere at the same time. It happened here. So this space here was at the Big Bang. So when we look at the distant galaxies and we see that they're flying away from us, that's not because they were flung out in some massive explosion at the beginning of time. It's because space itself is stretching, and it's been stretching since the Big Bang. The universe we see today is a network of galaxies spanning almost 100 billion light years. But remarkably, a blueprint for this astonishing structure is written into the very first light released into the universe. Even more remarkably, it's a blueprint that we can read today. This first light is no longer visible, but it's there. You just need to know how to look for it.
Well, this sea of shifting sand is the Namib Desert, the oldest desert in the world. And as the wind blows the sand off the top of the dunes, this landscape is constantly changing. This world has been sculpted by the sun. It drives the winds that shape the dunes, and its light paints this place a deep orange. But even when the sun disappears completely, this desert is still awash with light and colour. We just can't see it. Visible wavelengths of light are just a tiny fraction of all the light in the universe. Beyond the visible spectrum, our world is illuminated by invisible light. This sand has been under the full glare of the sun all day, and I can feel the heat radiating off it. Well, heat is nothing more than a form of light, although we don't normally call it light. It's actually infrared light. And the only difference between infrared and visible light is the wavelength. Infrared has a longer wavelength than visible light. Infrared isn't the end of the story. There are even longer wavelengths of light. Throughout most of human history, we've been blind to these more unfamiliar forms of light. But to detect them, you don't need a billion-pound satellite or a telescope built into the side of a mountain. You just need one of these, a radio. Because when we tune a radio, we're tuning in to a form of light, radio waves. But detecting them and understanding them provides the key to understanding the origin of the universe. And when you detune the radio a bit, you can just hear static, but about 1% of that static is music to the ears of a physicist, because that is stretched light from the Big Bang. So that sound is the sound of the first light released at the beginning of the universe. The reason we can't see this ancient light is because as the universe expanded, the light waves were stretched and transformed into radio waves and microwaves. This first light is called the cosmic microwave background, or CMB. The CMB fills every part of the universe. Every second, light from the beginning of time is raining down on the surface of the earth in a ceaseless torrent. If my eyes could only see it, then the sky would be ablaze with this primordial light, both day and night. These waves have been travelling towards us for over 13 billion years. They are messengers carrying information about the origin of our universe. In 2001, a satellite called WMAP took a photograph of our entire sky to capture this ancient light. The image reveals that the blueprint of the entire universe was created moments after the Big Bang. Well, this is one of the most important images of the sky ever taken in the history of science. It doesn't have the beauty of a spiral galaxy or a nebula, but to a scientist, to a cosmologist, it is the most beautiful picture ever taken.
because it contains a vast amount of information about the very earliest history of our universe. When the CMB was first detected, it appeared that the universe was exactly the same in all directions. But WMAP shows us that the early universe was far from uniform. Some areas were denser than others, and it's these ripples that seeded all the structure in the cosmos. The explanation for those ripples in the CMB is absolutely mind-blowing, because it's thought that they originated in the first billions of a second after the universe began, when the whole observable universe was billions of times smaller than a grain of sand, and little fluctuations called quantum fluctuations made little bits of the universe a bit denser. Those dense regions then got denser and denser as the universe continued to expand, and they seeded the formation of the first stars and the first galaxies in the universe. The early universe was a hot, almost uniform sea of matter and radiation. As the universe expanded, the slightly denser regions became increasingly dense. Atoms clumped together to form the first structures. Over time, these structures grew so massive that they collapsed under their own gravity. Hydrogen fused, releasing enormous amounts of energy. $200 million years after the Big Bang, the first stars in the cosmos burst into life. Darkness was banished, and the cosmos began to fill with light. Planets formed and fell into orbit around the stars, and these young solar systems orbited the galaxies. And the only reason why any of this exists is because of those tiny density fluctuations that appeared when the observable universe was smaller than a grain of sand. Without them, there would be no planets or stars and no galaxies. Our universe would look the same in every direction. Billions of years, generations of stars lived and died. And then, 9 billion years after it all began, in an unremarkable piece of space in the Orion spur of the Perseus arm of a galaxy called the Milky Way, a star was born that we call the Sun, that illuminated our embryonic solar system with light. So the light from the star that bathes the Earth has its ultimate origin in the tiny ripples that appeared in the first moments of our universe's life. By capturing the light from the skies, we've been able to tell the story of the universe's origins and evolution, and it's worth reflecting on what a remarkable thing that is. Little beings like me scurrying around on the surface of a rock on the edge of one of the galaxies have been able to understand the very origin and evolution of the universe. But there's one more twist to this story, because that ability to use light, to capture it and use it to understand our world, may have played a key role in the emergence of complex life on Earth. This is the Yoho National Park in the Rocky Mountains of Canada, one of the most spectacular mountain ranges in North America. A 100 years ago, a fossil field was discovered here at the Burgess Shale that may reveal how light shaped life on Earth. Well, this is one of the most important fossil sites in the world. I mean, actually, it's one of the most important scientific sites of any kind. And it's not just because of the number and diversity of animals you find fossilised in these rocks. It's because of their age. These fossils are over 500 million years old. There is virtually no record of complex life on Earth before this time. I mean, it's as if at one instant in this time we call the Cambrian era, complex multicellular life suddenly emerged, almost intact, on the planet. It's called the evolutionary Big Bang. Well, this is one of the beautiful animals you find up here in the fossil beds. It's called a trilobite. It's a very complex organism. It's got an external skeleton, it's got jointed limbs, but perhaps most remarkably, these, because these are compound eyes. They're very sophisticated, and this was one of the first predators to be able to detect shapes and see movement, and it could successfully chase its prey. These creatures were among the first to harness the light that filled the universe. Before they emerged, the rise and fall of the sun and the stars in the night sky simply went unnoticed. Now, there is a speculative theory that the emergence of the eye actually triggered the Cambrian explosion, this evolutionary Big Bang. Because once one species got eyes, then other species had also to develop eyes to either chase them as predators or evade them as prey. And that led to an evolutionary arms race. More and more complex life forms developed. So the evolution of the eye may have played a fundamental role in the emergence of complex life on Earth, and could have led to the evolution of our species. See, this little thing, although it looks unimpressive, may be the most important animal that we've ever discovered in our history. It's called a pikaia, and it's a little worm-like creature, but it's thought that this is a chordate, and that is the branch of life that we're in. So it could be that this is our earliest known ancestor. What's also fascinating is it's also thought that this may have been able to detect light. It may have had primitive cells that were sensitive to light and allowed it, in a very loose sense, to see. And if that's true, then this little guy may be our direct ancestor, and those little cells may be the things that evolved over hundreds of millions of years into our eyes. Without pikaia, we may never have evolved and developed the ability to see how this story unfolded. Understanding the universe is like a detective story, and the evidence has been carried to us across vast expanses of space by light. We've even been able to capture the light from the beginning of time, and we've glimpsed in it the seeds of our own origins.
Come with me and you'll read in a world of pure imagination. Take a look and you'll see into your imagination.
And we've seen things our ancestors wouldn't believe. Stars being born in distant realms. Alien worlds created by gravity. And spectacular galaxies frozen in time. But we are not mere witnesses to these events. Because the story of the universe is our story. We've learned how the dust of the stars makes each and every one of us, how a simple universal chemistry set makes everything we see. We've explored how the secrets of deep time shape the destiny of the universe and marvelled at the brief flickering moment in which life can exist. And we've seen how stardust falls to build the grandest structures in the universe. We know all this because of messages carried on beams of light. And isn't it a wonderful thing that these biological light detectors that first emerged 500 million years ago in the Cambrian explosion have evolved into those most human things, our green, blue and brown eyes that are able to gaze up into the night sky, capture the light from distant stars and read the story of the universe. There's a force of nature that's baffled the most famous names in the history of science. Galileo laid the foundations, but didn't get any further. Newton thought it was the work of God. And even Einstein, Albert Einstein, failed to solve it. It's a mystery that lies at the heart of everything. From the Big Bang and the beginning of time, to the existence of life on Earth. From strange distortions in the cosmos to the smallest stuff of matter. It's a puzzle that's led to the most abusive slanging matches in modern science. But I think that within my lifetime, we may succeed where many of the greatest brains in history failed, and finally solve one of the biggest mysteries of the universe. I'm Brian Cox, particle physicist.
I have one of the best jobs in the world. I have to find out what are the fundamental building blocks of the universe. How do they stick together and how do they work? And with a bit of luck, find out why they're there at all.
I've spent the last 10 years looking at the smallest stuff in the universe. But I'm interested in the biggest questions you could possibly ask.
Why do I exist? Why did you exist? Why is the Earth the way it is? Why is the universe the way it is?
Why is the universe built in a way that life can exist at all? At the root of all these questions lies a force of nature that surrounds us, penetrates us, and binds the galaxy together. The key to a much deeper understanding of the universe, and even our place within it, is gravity. It was gravity that made our sun ignite 5 billion years ago. Without gravity, there'd be no planets, no stars, no galaxies, nothing. If we want to know why the universe is built the way it is, we need a complete understanding of this elusive force.
But there's something missing in our understanding of what gravity is and how gravity works.
Getting to the bottom of the problem has vexed scientists as far back as the ancient Greeks. But in the late 1600s, in a small village in Lincolnshire, the question of gravity was tackled head-on by one of the granddaddies of modern physics. This is the home of Sir Isaac Newton.
Film about gravity, apple. It's a cliche, but the story goes that it was in this orchard that Newton was sat thinking about the universe, and an apple fell on Newton's head and got him thinking about what it is that makes the apple fall, what force pulls the apple towards the ground.
Newton suggested that the apple falls because of a force of attraction that naturally exists between the apple and the earth. It's this force that we know as gravity.
But Newton's real genius was not to just stop with the apple, but to ask the question, is the same force that causes the apple to fall here on Earth also responsible for the movement of much bigger things out there in the cosmos?
Newton believed that gravity is a force that acts throughout the entire universe. In 1686, he finally managed to break it down into one single mathematical equation.
Newton's understanding of gravity is actually incredibly simple. That the force between two objects depends on only two things: the mass of the objects and the distance they are apart. So the more massive the objects, the stronger the force, and the further the objects are apart, the weaker the force. See, it's easy to show, actually. Get a pen. So this is Newton's law of gravitation. The force is equal to the masses of the two objects divided by the square of the distance apart of the objects, and then there's Newton's gravitational constant that just sets the scale. It tells you the overall strength of gravity. With one beautiful bit of maths, Newton had figured out gravity, but not just here on Earth. The moon seemed to orbit the Earth exactly as he predicted, as did the planets orbiting around the Sun. Newton believed we live in a universe in which, ultimately, the movement of everything can be predicted. Newton's universal law of gravitation is one of the most important turning points in physics, and that's because it really is universal. It allows you to predict not only how things move under the influence of gravity here on Earth, but how the stars and planets and even galaxies move all the way across the universe.
Ignition sequence time.
Nearly 300 years after the falling apple, it was Newton's ability to predict how the moon orbits the Earth that allowed us to take a giant leap.
One small step for man, one giant leap for man.
Newton's law of gravity was crucial in allowing us to navigate from the Earth to the moon. But we now know Newton isn't entirely correct. I've come to El Paso in Texas, right on the Mexican border. I'm here to discover what's wrong with Newton.
Where are the keys?
No, we're ready. Now you're stopping us.
Because it's coming.
We're heading off across America to try and solve the mystery of gravity.
I think the most exciting thing we've ever done as the human race is to land on the moon. And it's, it happened just in my lifetime. I was about just over 1 year old when Armstrong and Aldrin touched down. So I don't remember it, but what I remember is growing up with it.
Back in '69, Neil and Buzz left more than footprints behind. They offloaded a special set of mirrors that could be used to test Newton's theory of gravity. Those mirrors have played an important role here at one of the last surviving outposts of the Apollo space mission. This is the McDonald Observatory, 4 hours drive from El Paso. We've arranged to meet up with veteran Apollo scientist Peter Shalis.
This is one of the photographs which shows this reflector package. This is a set of mirrors which are very specially constructed, so any incoming ray of light gets reflected exactly back. The reflector on the moon is really only about 18 inches square, not very much larger than this photograph. You can see some of the footprints. You can see a sandwich bag left on the surface. I don't think that was anybody's lunch.
The mirrors left on the moon allow Peter to make a very accurate measurement. Using a telescope with a built-in laser, Peter can precisely measure the distance from the Earth to the moon.
We orient the telescope so that it is facing the moon. The laser light coming out of the telescope then goes directly up to the moon. It can be reflected by the reflector, and it then comes right back through the tube again, makes its way through the optics, and we sense it inside the building.
Okay, there it is. Look at that. There's a really big crater. You can see the shadow.
Timing how long it takes the laser beam to go out and bounce back, Peter can precisely calculate the distance to the moon. But trying to hit that tiny mirror so far away requires very careful alignment and a bit of perseverance.
We may send out 1,000 million billion photons, whereas coming back into the telescope might be 10 or 5 or none. So it is still a very hard experiment because everything has to work just right.
How accurately can you make that measurement off Neil and Buzz's reflector and back again?
1 to 3 centimeters.
Over a quarter of a million miles.
Over a quarter of a million miles out, a quarter of a million miles back.
By taking accurate measurements of the distance between the Earth and the Moon, day after day, year after year, for nearly 4 decades, an incredibly precise map of the Moon's orbit has been produced. But the results have thrown up something very odd. The actual orbit of the Moon is different to that predicted by Newton.
It turns out that simple Newton's laws of gravity really don't answer all of the questions. For the data that existed, it was good. Newton really had a good formula. But as we get better and better data, we find that that's not exactly right.
If you use Newton's law of gravity to predict where the Moon should be, then the Moon is in the wrong place. Peter's results disagree with Newton's by about 10 meters. That may not sound much, but it means Newton got it wrong.
You've got to explain your observations, and Newton's gravitational theory just doesn't do it anymore. The observations are so accurate that we need something else.
This is an amazing result. We've relied on Newton for 300 years. His equations certainly appear to work really well. Yet it seems that there's more to gravity than Newton realised. Newton's understanding of gravity was good enough to allow us to fly from the Earth to the Moon, to cross 250,000 miles of space, to land on the Moon, and then fly all the way back again. But it's kind of got to make you laugh to think that you can go all the way to the Moon and back using something that's ultimately just an approximation. To find out what on earth is wrong with gravity, we need to go beyond Newton. The problem lies not so much in what he understood, but in what he failed to why gravity exists, or even how it works. Just allows you to calculate things. And Newton knew this, of course. He essentially just said that it's down to God. In fact, he said that the most beautiful system of the sun, the planets and the comets could only proceed under the dominion and counsel of an intelligent being. In other words, I'll give you the tools to calculate how the objects move around, but don't ask me how or why that is. That's down to God. To solve this fundamental flaw, we've got to take gravity out of the hands of the divine. We've got to discover for ourselves how gravity works. But our journey has only just begun. We've still got a long way ahead of us.
Set out at 3 o'clock, we were doing by 4, we'd only lost 2 men.
It's not about giving information anymore, it's about them feeling the journey.
It's brilliant! Driving across the desert to do physics!
Our quest has brought us to Kitt Peak, about 80 kilometers west of Tucson in southern Arizona. Since the first telescope was built here back in the 1950s, this mountaintop has witnessed some of the most important discoveries in cosmology. Kitt Peak is one of the most famous observatories in the world. It's the place where, about 30 years ago now, something very strange was observed about the fabric of the cosmos. We've come here to see a little piece of the night sky, 7.8 billion light years from Earth. That little piece of sky has given us a glimpse into the inner workings of gravity. But outside, the weather's not good. They're not opening the telescopes tonight. But here's what they saw all those years ago. Astronomers are looking into the sky to find distant galaxies, billions of light years away. And they found this. At first sight, it looks like 2 different galaxies. In fact, they gave them different names, 957 and 561. When they looked more closely, they found that they look identical in every way. It's incredibly strange. It's almost like there are 2 twin galaxies. But actually, they found that the light was absolutely identical from each one, and they're the same distance apart. The interpretation is, this is a picture of one single galaxy. This certainly confused the astronomers. But they soon realised that the cause of this strange cosmic mirage had been predicted nearly 100 years ago. There's one man who, for me, really did think outside the box. He was the first celebrity scientist, hailed by many as the greatest physicist of all time. At the turn of the 20th century, it was Albert Einstein who opened our minds to a completely new way of looking at the universe. Einstein's universe is made of something called space-time. Now, space is what we see around us. It's got length and breadth and height. And time, well, it just ticks along. But in Einstein's universe, they're woven together into a fabric. Space and time are not separate, they're one and the same thing. And that fabric is called space-time. This strange idea of space-time is certainly radical. In one sweeping action, Einstein's theory of relativity completely changed our picture of the universe. Newton's universe was kind of a stage, an arena in which everything happens. It was like a box, exactly as you'd imagine it, and the stars and the planets and us are just going about our business inside the box. Now, Einstein's genius was to realise that you don't need a box, there's just space-time, and everything that happens in the universe affects the space-time, and the space-time affects everything that happens in the universe. In Newton's universe, there's just empty space. The stars and galaxies have an effect on each other, but that's it. Einstein's universe is completely different. It has an internal fabric, the space-time. The celestial bodies are all embedded within this fabric, and they all interact with it. In Einstein's universe, the planets, stars and galaxies actually warp, bend and distort the space-time. It's this interaction of matter with the fabric of the cosmos that helps explain the weird sightings on Kitt Peak. That image of duplicate galaxies can be explained by the bending of space-time. What's happening is that light from a distant galaxy is passing by a galaxy or even cluster of galaxies on the way to the Earth. And in that cluster there could be millions or tens of billions of stars, huge amount of mass which bends and curves the space. So the light from the distant galaxy curves around the cluster. And from our perspective on Earth, this bending action causes us to see multiple images of the distant galaxy. This explanation has far wider reaching implications than simply describing strange astronomical oddities. It lies at the very heart of Einstein's understanding of gravity. Einstein believes that it's this bending of space-time that actually explains gravity's existence. Einstein didn't see gravity as Newton did, as a kind of force of attraction between two bodies, a star and a planet, for example. He sees gravity as a result of space and time, of space-time being bent. Einstein says that our planet is distorting the space-time. And it's this curving of the fabric of the universe that creates the effect we feel as gravity. The bigger the mass, or the nearer you are to an object, the more curved the space-time becomes, and so the stronger is the effect of gravity. It sounds impossible to prove, yet the fact that space-time is distorted by the Earth is something many of us have to contend with every day, whether we know it or not. Einstein's understanding of gravity is crucial for the correct working of one of the most useful innovations, or GPS.
Right turn in 1.9 miles.
We're heading to GPS headquarters just south of Denver, Colorado, but we're running a bit late.
Approaching U-turn.
We'll be using a GPS satellite navigation system wherever you go in GPS headquarters. Did you get there on time? No, right, lost.
This is the Schriever Air Force Base in Colorado Springs. It's a maximum security military installation. It's an Air Force base without a runway. It's the home of the Global Positioning System. Half an hour late, and we're quickly taken under the wing of Major Bandit Grant.
Gentlemen, well, welcome to the 2nd Space Operations Squadron. Give you a tour as we walk down through here.
It's from this one room that the whole GPS network is controlled. Running the floor today is Captain Chris Maddox. You must have the biggest impact of any military crew in the world on ordinary people.
Typically, civilian users aren't really our first thought because I'm a warfighter. We think, bombs on targets, planes landing safely, the soldiers not getting lost in the desert. But secondary to that, we do think that there are people using, Sam or Tom. All these users have the ability to get from point A to point B because of what we do.
The global positioning system works by using a fleet of satellites orbiting the Earth. It's these satellites that are ultimately controlled by the American military. How many satellites have you got up there?
We have 31 satellites in the constellation right now. The minimum for the constellation is 24 satellites.
So you can afford to lose 7?
Hopefully not. But
on your watch?
Hopefully not.
For the controllers of the GPS, time is everything.
U.S. Naval Observatory Master Clock has its own mountain daylight time, 18 hours, 48 minutes, 5 seconds. U.S. Naval Observatory Master...
For the global positioning system to work, the clocks on board the satellites have to be exactly synchronized with time on Earth. But for the satellites orbiting 18,000 kilometers above our planet, Einstein predicts something very strange. He predicts that in orbit, time itself runs at a different speed to that on the Earth's surface. It's incredible for anyone to suggest that time goes at a different rate on the ground than it does in space. What's the difference? Well, the difference is gravity. The closer you are to the Earth, the stronger the gravitational field. The further you are up into space, the weaker the gravitational field. What Einstein said was that the stronger the gravitational field, the slower time ticks. The weaker it is, the faster time ticks. The link between the speed of time and the strength of gravity is all down to Einstein's prediction that the Earth distorts the space-time. If you put something heavy in space, like a planet, a star, the Earth, then that heavy thing bends the space, it curves the space. But space and time are intimately linked. So does the Earth also bend time? Well, yes, it does. In the reduced gravity up in orbit, time really does tick a bit faster than time on Earth. To keep everything in sync, the controllers have to dial in a time correction.
3 past 35.
That's 1 6, step 2, go.
Step 4, it's good order, no windows.
Step 6, ascension's updating on the B string. Attack won't come up, it comes good.
You have good visibility at Ascension until 2152 and good old Viz at Diego, no open jobs.
You've got to allow for the fact that time runs at a different rate on the ground than it does in orbit. If you don't, then your GPS system will drift, not by a few centimetres as you might think, but by 10, 11, 12 kilometres a day. This morning we got last year didn't work. Can you believe that? That it took us into a field about a mile away.
Our response to that is the constellation is healthy and producing an accurate navigation signal.
What you actually mean is you are an idiot. With that, it's time to leave.
Calculating route. Approaching U-turn.
You going wrong?
The fact that GPS operates in the way it does
shows that Einstein's idea of bending space-time is an accurate description of how gravity works here on Earth. But Einstein's understanding of gravity is not complete. Something is missing. It may hold true for the Earth and the other planets, even for the movement of galaxies. But Einstein knew that his theory of gravity doesn't apply to the whole universe. It fails to work in the most violent and turbulent places in the cosmos. But if we want a complete picture of the universe, we must know how gravity behaves everywhere. We've come to America's deep south, not far from New Orleans. These are the famous bayou swamplands of Louisiana. It's out here that scientists are trying to peer deep into the darkest and most brutal corners of the universe.
Louisiana is one of those places that you always think of as being, laden with black magic and things. That's certainly not a rational exploration of the universe.
In these alligator-infested backwoods, the final piece in the puzzle of Einstein's universe is being put to the test. This place stands at the leading edge of the exploration of gravity. Joe Gianni is the head man.
Gravity will probably and hopefully confuse us for a long time before we figure out what it really is. And scientists are happy when they're confused and hot on the trail of something fun.
Rising out of the swamp in the shape of a giant L, this is the Laser Interferometer Gravitational Wave Observatory, or LIGO for short.
Any signal we see is going to be from something really, really interesting and cool. Data from those kinds of sources would be really valuable to learn things about gravity and the nature of gravity.
This machine was built as an observatory, a chance to witness violent galactic events beyond anything we've ever seen before. One of the things I hope to see is when you get two stars called neutron stars. Now, a neutron star is probably twice or three times as heavy as the Sun, but compressed into a ball about 10 kilometres across, so the size of a city. And there are places where there can be two of those things orbiting around each other at about 100 or even 1,000 times a second. The incredibly dense neutron stars spin round each other, churning up the space-time. As they spiral in, going faster and faster, Einstein predicts this sort of violent cosmic event will create something called gravitational waves. But what exactly is a gravitational wave? It's not that easy to describe. If a wave came through this room, it'd, what did I say? Ripples in. Space-time isn't just something that's, up there amongst the stars. It's here, right? It's in front of me and it's inside me. So when I move, I disturb it. I send out ripples in it. It's just like if I jump into a swimming pool and start swimming, I'll send out ripples on the surface of the water. It's the same with space-time. In theory, these waves would cause space and time to stretch and shrink as they pass through the universe. These waves are physical distortions in our reality. They really are stretching and contracting the space and the time that we're in. But trying to see these gravitational waves using the LIGO machine is proving very difficult.
Gravity waves cause lengths to change in one direction differently than the other direction. So if I were very stretchy and a gravitational wave were going through me, this is what would happen. I would get shorter one way and longer the other way.
The machine works by using a laser beam to measure the distance between two sets of mirrors suspended at the ends of the two 4-kilometre long tubes.
So from up here you can see pretty much all the key components. You can see running off to the right there and also running down under our feet are tubes that carry the light to the end station. So there's a mirror here and there's a mirror 4 kilometers over that way. And when the gravity wave comes through, the distance between those mirrors changes.
They're basically just fancy rulers.
That's right, that's right.
But even after 5 years in continuous operation, the team hasn't been able to observe any violent gravitational hotspots. This is because they still haven't detected Einstein's elusive gravitational waves.
This is one piece of nature we haven't really observed right yet, to see gravitational waves, whether they really affect things here the way we think they do. We don't know where the sources are that we're looking for, so we have to look farther and farther out until we catch one.
In the most extreme places in the universe, Einstein is still on dodgy ground. As we travel deeper into space and time, we're beginning to realise that Einstein's universe may... But to know the cosmos, we need to know how gravity works everywhere. In the most sinister of cosmic phenomena, in the dark heart of a black hole, Einstein has no answers. And his idea of gravity completely fails in the most violent event in history. At the Big Bang, the origin of everything, the universe was incredibly hot, incredibly dense, and incredibly small. All matter was condensed into a space smaller than a single atom. And here lies the problem. Much as he tried, Einstein never managed to answer the question of how gravity works when things get very small.
Einstein gave us a beautiful theory of gravity. It tells you how planets orbit around stars, it tells you how galaxies orbit around each other, it tells you how the universe evolved. But Einstein himself knew there's a problem right at the heart of the theory. Einstein's theory of gravity doesn't work at all if you come into the world of the small, so the subatomic particles that make up my body. Einstein's theory has nothing to say at all about gravity in the realm of the atoms, molecules, and subatomic particles that make up the world.
This is Einstein's greatest failure. His calculations just come up error. At the smallest scale, his whole theory simply falls apart. But we have to know how gravity works at the smallest distances if we want to know how it all began.
Einstein's theory of relativity just can't provide the answer. The maths just doesn't work on the smallest distance scales. So the answers probably won't lie up there in the realm of the galaxies. In here, in the world of the atom, the stuff of matter.
This is the world of quantum mechanics, which is what I do for a living. It's in quantum theory that we hope to find the answers that Einstein searched for to his dying day, to understand how gravity behaved at the very beginning of time.
If we can figure out how gravity works at the level of the smallest subatomic particles, then maybe we can finish what Newton and Einstein started and form a complete picture
of this mysterious force of gravity. To achieve this goal, we have to try to recreate the conditions of the Big Bang here on Earth and peer deep into the heart of the subatomic world. This place is Fermilab, and I used to work here. It's home to the TEVATRON particle accelerator. The TEVATRON basically works by bashing stuff together and seeing what comes out. What we do is we take protons and accelerate them around that way, and antimatter protons, send them around that way, and they pass by here 50,000 times a second, very close to the speed of light. And then we collide them together, we smash them together. It's through collisions like these that the nature of matter has been revealed. But the force of gravity still sits outside what we know. One of the ways we might get to the truth about gravity is to try and fit it into the beautiful framework we have that describes the subatomic world. Quantum mechanics predicts that the force of gravity should be transmitted by a particle. We call this particle the graviton. If we could just find these gravitons, then we might at last arrive at a quantum theory of gravity, a universal theory that will work everywhere in the cosmos. For 8 years, Greg Landsberg has been using Fermilab's particle accelerator to try to create gravitons.
These particles, well, we haven't quite seen them, so what I'm telling you is we haven't quite seen them. That's right, it's our hypothesis, so we don't quite know if this is true or not. It's not that we can shine light on gravitons to see them, so we have to find some other means. It's amazing that the way to see the graviton is by not observing it, by observing its missing.
To see something that's missing, Greg is effectively looking for missing energy. Typically, when you bash things together, the energy of the original particles should be the same as the total energy of all the particles coming out. But if you were to make a graviton in that collision, then our detectors are certainly not capable of seeing it. So the graviton will take energy away from the collision. Energy will appear to disappear.
So what this picture tells us, it's called event display. The height of these bars is how much energy is released in this collision in that particular direction.
You've got a collision in the middle there, and there's stuff spraying out.
So what we're trying to do is to sum all this energy to see if something is missing. If you look at this display, you see a lot of energy going in this direction, but very little on the other side. And this yellow bar, in fact, represents the fraction of energy which is missing.
All right, so you see that, that means there's something escaped.
That's right.
If gravitons are created, Greg believes the reason why they would disappear is because they vanish into a place beyond our reality, into some sort of extra dimension. Now, we're all familiar with the 3 dimensions of our world, as up and down and north and south and east and west. But what scientists like Greg are proposing is that there can be extra, hidden, unseen dimensions. It sounds ridiculous, and it is impossible to picture, but theoretically it's possible. And it's also possible that gravitons, the particles of gravity, can spend most of their time in those extra dimensions.
If gravitons really are created and they escape in these extra dimensions, we would never see them. So it might sound like a very odd hypothesis, an odd concept, really nothing prevents us of thinking in this direction, especially if we can solve these mysteries.
The graviton may really be the final piece in the puzzle. Newton could predict the effects of gravity, Einstein worked out why it exists, but by finding a graviton, we might at last truly understand gravity.
Does Greg stand any chance in finding his graviton?
You know, it's still just possible. I mean, when this machine started up, it was very possible, but it seems now that probably the Tevatron is just too small to do it. So we're going to all move, I mean, myself, Greg, and pretty much everyone that works here, certainly in a couple of years. We're going to all move to Geneva, where we've built one of these machines, but a lot bigger, and then the search will continue. We now know exactly where we stand in our quest for a complete explanation of gravity. The solution to a deeper understanding of gravity will certainly lie in the world of the small, the quantum world. It's in the marriage of Einstein's theory of gravity with the quantum theories of subatomic particles. But nobody has any idea just how long this might take. We could see something at a particle accelerator tomorrow that shows us the way to our quantum theory of gravity. Or some Einstein, some Newton, some Galileo, some Da Vinci could just appear on the scene and simplify everything. Understanding how gravity works everywhere in the cosmos, and crucially at the beginning of time, will bring us ever closer to a theory of everything. Knowing gravity will mean that we can better understand why the universe is built the way it is. And that's surely the biggest question you can ask. But the journey that lies ahead is not going to be easy. If there are things that I listen to, you listen to, that you think, well, it's just, I don't understand that, then you're in good company because nobody understands it. You dig deeper and it gets more and more complicated and you get confused and it's tricky and it's hard, right? It's hard, but it's beautiful.
The laws of gravity are very, very strict, and you're just bending them for your own benefit.
Horizons back on BBC Two next Tuesday at 9.
The Conservative leader punishes the MP accused of putting his sons on the payroll, but how many other MPs are using public funds to pay relatives?
We've been riding that heresy of his. I hope he's going to unveil a death ray. I don't know.
I'm going to make at least one unsuspecting celebrity do sums.
I really don't tend to look my gaze. It's the worst thing that's happened to me as an adult.
The only thing I do know is that I've been roped in to go up on stage with Simon Pegg, no less, waving a rope about.
I can see why you've got no hair.
There it is, there it is. I'm so thrilled to have been asked to be honest, so I don't do clever things.
There's a real buzz in this room and it just makes me feel proud to be a scientist in this day and age.
Perhaps tonight is my chance to get it together and realise what it's all about and have a big sort of dancing moment, you never know.
I'd like to ask Professor Brian Cox about his hair. So it's shared interest.
Maybe blow some stuff up.
Wow, you're right.
I'm hoping it's going to start simple for people like me and then get slowly more complicated.
Because otherwise, if my brain starts swelling inside my skull, it's just going to pop and I'll distract people.
Welcome to the Royal Institution of Great Britain, established in 1799 as an institution for diffusing knowledge and perhaps the most iconic lecture theatre in science. Thomas Huxley championed Charles Darwin's theory of evolution here. Michael Faraday pioneered our understanding of electricity and magnetism here. And on this stage, he demonstrated the first electric motor. And the great scientist and lecturer Sir Humphrey Davy, who was also the first director of the Royal Institution and one of my heroes, spoke here many times. And he gave the best explanation of the absolute need to do science that I know of. He said, nothing is so fatal to the progress of the human mind as to suppose that our views of science are ultimate, that there are no mysteries in nature, that our triumphs complete, and that there are no new worlds to conquer. Well, tonight I want to talk about one of the great mysteries, the great pillars of our understanding of nature, a scientific theory that underpins much of the technology we take for granted in the 21st century, yet retains its reputation for obscure difficulty and bizarre predictions. Now, by the time I've finished, I hope that while your view of reality might have shifted a little, you'll understand a bit more about how the universe works. Now let's start with the contents of this box. This is a rough diamond. It's worth well over £1 million. It costs so much because it's rare and because it's beautiful. But there's a different kind of beauty here, a more profound kind of beauty. Less superficial, but perhaps far more instructive. A diamond is one of the hardest known substances, which is why diamonds are widely used industrially. But light can stream through it relatively unimpeded. So there's beauty in a question, which is, how can something be so ethereal and yet be so hard that it can drill through solid rock? Well, to answer that, we need to know about the structure of the diamond, indeed the structure of all matter itself. And the best theory we have to describe matter is quantum theory. Now, I understand why quantum theory can seem a bit odd. I mean, it makes odd statements. It says, for example, that things can be in many places at once. In fact, technically, it says things can be in an infinite number of places at once. It says that the subatomic building blocks of our bodies are constantly shifting in response to events that happened at the edge of the known universe, 1 billion light years somewhere over there. Now, this is all true, but that isn't a license to talk utter drivel. See, quantum theory might seem weird and mysterious, but it describes the world with higher precision than the laws of physics laid down by Newton, and it's one of the foundations of our modern understanding of nature. It doesn't, therefore, allow mystical healing, or ESP, or any other manifestation of New Age woo-woo into the pantheon of the possible. Always remember, quantum theory is physics, and physics is usually done by people without star signs tattooed on their bottom. What makes quantum theory a good scientific theory? Well, it makes predictions that can be tested against experiment. And when we test those predictions, we find that they agree with observation. This means quantum theory is not wrong. It's a survivor, if you like, because it's been put to the test over and over again and consistently been found to make correct predictions. If this changes, then we'll search for a new theory. There are no absolute truths in science. This is how we make scientific progress, and this is how everything in the world that we take for granted was delivered. So remember that however odd it might seem, tonight I'm going to show you, hopefully, that quantum theory works. So I want to explain quantum theory to you in the simplest way that I can. Ultimately, I'll show you how it gives us insight into the fundamental building blocks of the universe and explains the existence of some of the most spectacular phenomena out there in deep space. And I'm going to do this now because if I don't point wistfully at the sky at least once, some of my viewers will get annoyed. So there you go. That's the only mountaintop pose I'm going to pull. So no helicopters tonight. To begin, let's zoom in to the heart of this diamond. What I've got here is a sequence of actual photographs of, well, initially the surface of the diamond, but these photographs have been taken by a series of increasingly powerful microscopes.
So as we zoom in, you see that at first you're seeing a more detailed picture of the structure of the surface of the diamond. But as we go right in, you see that a regular pattern, a regular structure emerges. So this is an electron microscope photograph of diamond. And what you're looking at here actually are carbon atoms, individual atoms. You see that they appear to be in a kind of a dumbbell shape, and that's a space and another pair, because you're looking at a two-dimensional image. But if you take that to 3 dimensions and look at this is the structure of diamond. And what you can see is carbon atoms surrounded by 4 other carbon atoms in a regular, beautiful crystalline structure. Now, in this diamond, this over £1 million piece of diamond, there are something like, 3 million billion atoms, and they're laid out in precisely this beautifully simple way. I should say actually this diamond is as it was when it was found, so this hasn't been cut. It was found in South Africa well over 100 years ago, and it's 3 billion years old. And that shape, that structure, this diamond shape, that's how it naturally appeared, because its structure is like this. It's built out of carbon atoms exactly like that. And carbon atoms can't be packed any more tightly together than this. And that's what makes diamonds so tough and allows them to cut through virtually anything. Which makes what I'm about to say quite remarkable. See, the atoms that make up this diamond, and pretty much everything else for that matter, are virtually empty. Now, what do I mean by that? Well, what is an atom? Well, about 100 years ago now, in the greatest city known to civilization, which is Manchester, Ernest Rutherford discovered that the atom consists of an atomic nucleus, which is made of particles called protons and neutrons tightly packed together, and a third kind of particle called electrons orbit somewhere or exist somewhere around the outside. The nucleus, protons are positively charged, neutrons are neutral, so it has a positive charge. The electrons, somewhere out here, have a negative charge. And as Faraday would have talked about on this very stage just under 200 years ago, there is a force that holds the electron to the nucleus because they're both electrically charged. So that's kind of a sketch, a schematic view of the atom. We've known that now for around 100 years. Protons, neutrons and electrons. These 3 particles make up not only the diamond, but everything we can touch, every structure we can see. Everything is made up of these same 3 absolutely identical particles. So the richness of the natural world, everything on planet Earth, everything we can see beyond, is described by a simple recipe that determines how these simple particles combine together. Now clearly physicists don't call it a recipe, we call that quantum theory. Now historically, one of the first great challenges for quantum theory, indeed one of the reasons that theory was developed at the turn of the 20th century in Manchester and a few other places, was to understand precisely how these particles come together to create this diamond, you, me, and everything else. And 100 years after its discovery, it still provides our best understanding of the structure of matter. And admittedly, yes, it is still a bit strange. Now, one of the particularly strange things about it is the behaviour of electrons inside atoms. So these imperceptibly tiny electrons spend their overwhelming majority of their time in far distant clouds. So between the nucleus and the electron, there is a vast emptiness. If I were a nucleus and I perched on the edge of the White Cliffs of Dover, then the fuzzy edge of the electron cloud will be somewhere in the farms of northern France. You're looking out towards the electrons, I'd see nothing but empty interatomic space. So atoms are vast and they are empty. Actually about 99 point, I've got to count this on my fingers, 99.99999999999% empty. It's 13 nines. So you buy this diamond and you buy in about £1 million worth of mainly empty space. And since everything is made of atoms, that means you are vast and empty too. I mean, especially you. No, I can't say that. Never say that to a stand-up comic. What am I doing? If I squeezed all the space out of all the atoms in all the people on the planet, then you'd be able to fit the whole of humanity into that diamond. And that's how empty matter is. So understanding why atoms are empty and yet so solid? Why light can stream through that diamond and yet it sits nicely on the predominantly empty cushion and the predominantly empty floor is therefore a prerequisite to understanding the structure of everything in nature. Now, already you might have gathered that the world inside an atom must be a strange place where things don't behave much like they appear to behave here in the macroscopic world. But there's one historic experiment which contains everything you need to know about the bizarre way that particles behave, and therefore why atoms are the way that they are. Now, I'm going to need a helping hand for this. I know that Sarah Milliken, there we are, has volunteered kindly to help me. Where's Sarah? There's Sarah. So Sarah, would you mind? Did you do a science degree, by the way?
No, I've already been asked that by somebody in the audience. Did you study physics? No, I just sort of gave up after GCSE. Is that a problem? Should I go back to my seat?
All right. Anyone that volunteered? So you may or may not have heard of the double slit experiment. It's certainly something that every physicist, every physics student...
I've heard of it, but it was something different.
Was it? Well, we're going to... Every physicist has kind of gets taught this the moment they step through the doors of the university. It's simple, and it demonstrates the paradoxical world of quantum particles. So first of all, we're going to do it. We're going to do it actually twice, or even 3 times. So I'm going to give you this bucket of sand, which is quite heavy actually, so first I'll explain what to do with it. So these are particles of sand, little bits of sand. They're probably your picture, I suppose, of what a particle might be, a little piece of matter. And so what I'm going to ask you to do is just pour the sand onto this piece of board, which has just got 2 slits cut in it. And I suppose before I do it, I can ask you what you think will happen to it. Yeah, go on, you pour it first, and then I'll ask you what you think might happen.
Let's chat for a while while I'm holding the bucket.
It is fun, doesn't it? So just pour it through the slits. Now, what do you think is going to happen? So we're just pouring particles of sand over the slits. Let's keep going. So there we are. That'll do. That'll do, I think. So if I remove that, what does that remind you of?
I feel like smacking it. Does that help?
Yeah, pour that sand into that. So that's probably pretty much... Okay, you can put it down now. That's probably pretty much, I suppose, what you expected would happen. Like the sand has just fallen through the slits, and beneath each slit there's a bigger pile of sand. Particles fall through slits, pretty obvious. But this is a picture of real data. So this is real experimental data of electrons essentially being poured through 2 slits. So it's electrons being fired at 2 slits, and then there's a screen there. And so what you're seeing really is just piles of electrons. So the white spots really are where electrons hit the screen. So there's a pile, and then there's nothing. And then there's a pile, and then there's nothing. A pile, and then there's nothing. Looks absolutely nothing like that. But the experiment was the same. It really is electrons being poured through 2 slits onto a screen, and you get that strange pattern. So, let me show you this, which is a different version of the same experiment. Now this is a tank of water. So there's some water in there, and as you can see there's just a bar that's vibrating up and down, and then there's 2 slits.
Yes.
So you can see the 2 slits there. If you come around here, you can see, let me go on that side, you can see the screen here. So there's the 2 slits, and these are the waves of water. So there's a flat wave of water hitting the 2 slits, and then coming through the slits. And you can see that there are waves kind of here. But here, there's kind of an area where the water's flat.
Yeah.
And then here there are waves, and here's an area where the water's flat. And here are waves, and here's an area where the water's flat. So if I were to, I could sketch it actually on the blackboard. If I draw on that, we've got those 2 slits, like that, which you can see there. And then we've got the water wave coming through, and you can sort of see that the waves, when they go through the slits, spread out like that. And then we can see that at the front, what you're seeing is you're seeing kind of a place where there's no waves, and then there's some waves, and then there's a place where there's no waves, and then there's some waves, and there's a place where there's no waves. So you see that pattern on the front. So if you were to draw kind of a
detector along there, then you'd see that. Right? Because here you'd see nothing, so no waves, no electrons. Here you'd see the electrons, here no waves, here waves, here no waves. So what are we to infer about electrons?
Have you not done your homework today? Is that
No.
what it is?
I mean, this is just the experimental data. This was first done, by the way, in the 1920s, and it was a shock when it was seen. But the inference is that looks like that.
Because it could be a long game.
It's the same.
GCSE grade C, remember?
This pattern here. What do you think?
You should just tell us.
So the electrons are behaving more like the waves in the tank on the water waves.
Yes.
And that's a classic pattern you see when you get waves passing through slits, rather than this, which I suppose is what you might have expected electrons to do, because you might think of electrons as being little grains of sand. But actually, they don't behave like little grains of sand. The experiment tells us they behave more like waves on water. So,
exactly.
Thanks, Sarah. That's, physics. Well, this might all be a bit confusing as you just seen, but if you remember nothing else, remember this. The double-slit experiment reveals something fundamental about particles, like the electrons inside the diamond. Sometimes they behave like particles, but sometimes experiment says that they behave like waves. Now, there's a deep explanation for this, so I'm going to get to that a little bit later on, but for now, all we need to remember is that electrons behave like waves, and this is the key to understanding the emptiness of atoms. Simple? I hope so. So let's clear away the water tank. So, we've understood that electrons exhibit wavy behaviour, but how does that explain the emptiness of atoms? Well, I need some volunteers now, and I know that Simon Pegg and Jim Al-Khalili have kindly volunteered, so would you both like to come down?
That's right.
Have you seen him there?
Hello.
He's got an earpiece in. He's watching really carefully. So I've got an experiment for you to do involving a spring and your wrists. So what I'd like you to do is stretch the string a little bit, as far away as you can. Now what I want you to do is start gently oscillating the spring, but very, very gently.
Both of us?
Yeah.
Okay.
Well, you'll see what happens.
Okay.
Let's see what happens.
Up and down or longitudinally?
Up.
Shall I say about that?
Up and down. Up and down, Professor. Up and down. So just a bit more. There you go. Two. And a bit more. There you go. So what you're doing is vibrating the string.
Are you going to jump in?
It looks like painful, doesn't it? So what you're doing now, just gently vibrating the string, and notice that it's vibrating in a very particular way. So because you're holding it still there, and you're holding it still there, so it's trapped, it's confined in a sense. So what you can see is that there's only one bit which is moving with the maximum amplitude, if you like, the maximum wave, and it's in the middle there. So that's called a standing wave. It's called a standing wave because it's confined, it's doing nothing really, it's vibrating up and down. It's not a wave as you might usually expect it. Now if you give it a bit more wrist action. Look at that one. That is the next standing wave up. So there's a transition from the one where we're just moving here. This one's got 3 stationary ones.
Don't get carried away. This happens a lot. Sorry.
three stationary bits. There's one stationary bit there, one stationary bit there, one stationary bit there, and the amplitude, the maximum amplitude is there and there. Now you can get another one going. If you really try, which is the third one. There it is. That's got two stationary points, one there and one there. That's a brilliant.
No, it's gone again.
I can see what.
Hang on. There.
Two stationary points. Put 1, 2, 3, 4 stationary points. I can see why you've got nowhere.
There it is.
Right.
Oh, that's better now.
There's the fourth one. So you carry on.
Now it feels like someone else.
Oh, let's go. Stop.
So if I just carry on. If I just
There we go.
Yes. Perfect. 1, 2, 3, 4, right, you can stop now. Good practice. Thank you. For later. Thank you very much. I sketched what you saw there. You saw that one very clearly, which was this wave where there were just two stationary points, which were at the ends. And then you saw this one, where there are three stationary points. And then you saw this one, where there were four stationary points. And actually, because that's the best I've ever seen it done, there was one with about 5, I think, or even 6. So you saw that there were only certain waves that the spring could vibrate, certain ways it could vibrate, and the reason it behaved like that is because it was trapped at both ends. So this is what physicists would call standing waves, and you saw them appear on that spring. Now, what has that got to do with empty atoms? Well, just as this wave was trapped between Jim and Simon, electrons are trapped inside atoms. See, the positive electric charge of the nucleus effectively traps the negatively charged electron inside an atomic-sized box. And when an electron's trapped, just as the spring was trapped between Jim and Simon, it exhibits the same kind of wave-like behaviour as the spring. So now we're getting closer to understanding what's happening inside an atom. But what do standing electron waves around a nucleus actually represent? Well, the clue is that Jim and Simon had to put more energy in to switch from one standing wave to another. So it's tempting to think of those electron standing waves as waves with different energies inside an atom. Waves that the different energies the electron can have, if you like, when it's confined around a nucleus. And this turns out to be correct. But just as there were only certain standing waves on the spring inside an atom, there are only certain energies that electrons can have. Now, quantum theory allows physicists to calculate the shape of the waves, and therefore the allowed energies the electrons can have inside the atom. And when you do the calculations, you find the lowest energy wave, if you like. So I suppose this standing wave here that can fit around the nucleus has a wavelength of 3 × 10⁻⁻10 meters. Now let me just write that down, because you might be familiar with the notation. It's 1, 2, 3, 4, 5, 7, 8, 9. 0.0000003 of a metre, which sounds unimaginably small, but it's enormous compared to the size of the nucleus. It's actually about 250,000 times larger. So that is why atoms are so big and yet so empty. It's because electrons trapped around the nucleus behave like waves, in this case standing waves, and there has to be enough room to fit an electron wave around the atomic nucleus. But that doesn't answer a very important question. Now, we've shown why atoms are empty, but we haven't yet explained how they become so strongly bound together that they can create solid objects like our beautiful £1,000,000 diamond here. Answer that, and we explain the structure of everything we see in the universe. The early years of quantum theory were dominated by boy wonders. the early years of quantum theory were dominated by boy wonders, people actually half my age, believe it or not, so much so that it became nicknamed Knabenphysik, which translated into German means boy physics. Now the key discovery was made by a man called Wolfgang Pauli. Pauli published his first paper on Einstein's theory of general relativity when he was 18, and his great contribution to quantum theory was made when he was only 24. It's known as the exclusion principle. Now, we've seen that electrons can only exist in certain energy levels around the nucleus. These energy levels, essentially, associated with the different standing waves. Those energy levels correspond to standing waves that can fit in the atomic-sized box. But the key point that Pauli realised is that electrons can't all simply inhabit the lowest energy level. Now, to a physicist, this should look a bit odd. I mean, take this apple, for example. If I lift the apple up, then I have to do work, I give it energy to lift it up. And if I let go, so I don't support it anymore, then it falls to the ground. Now, the explanation of that for a physicist is that the apple is falling into a lower energy state. Nature doesn't like to be in high energy states. It wants to cascade down into the lowest energy configuration that it can. But the surprising thing is that electrons don't all live in that lowest energy level in an atom. It turns out that they're forbidden from doing so by an unbreakable law of nature. That law is called the Pauli exclusion principle. It's kind of like all of you sitting in these rows here. You aren't allowed to all come down to the front row. You can't all squash into the front seats because there isn't room for you. Electrons don't all occupy the lowest energy slots around an atom. Instead, they fill each level up in order of increasing energy. This might sound meaningless, maybe it sounds a bit abstract, but let me tell you that it isn't. See, Pauli's simple quantum rule is profoundly important. In fact, it's the key to understanding chemistry. But don't take my word for it. Time for another volunteer. And I know that James May kindly volunteered to take part in this. He looks very worried, so maybe he was never asked. But anyway, James. Now, this is doubly amusing for me because I know that you know exactly what's going to happen because there's a canister of hydrogen gas there, and I know you're a keen aviator, so you think about the story of the Hindenburg, which was unhappy, wasn't it? I think I get to wear the goggles. You might have to put the goggles on. It's only a small safety thing because it went wrong in rehearsal. So what we're going to do is we're going to encourage a small kind of chemical reaction to happen. So what we're doing is we're bubbling hydrogen through hydrogen gas through this soap here. And what I'd like you to do, actually just wet your hands first, just because again it's just a safety thing. It stops your hands catching fire. And actually perhaps roll your sleeves up a little bit. Oh, you'll be alright. I'm sure you'll be fine. So I'd like you to grab some of that hydrogen in the soap bubbles. How's that? Don't look at what I'm doing. What I'm going to do is I'm going to encourage a chemical reaction to happen from over here. Ow, you right? Thank you very much. Thanks, James. That actually was a lot more fire than I was expecting. Actually, I'm sorry about that. So what happened there? Well, what we did was we bubbled hydrogen gas into these bubbles. James held them, and then I just gave them a little kick of energy, which encouraged them to react with oxygen in the air. Now, if I draw the energy levels of oxygen, then they look something like that. They don't quite look as neat as I drew the standing waves on the spring. That's really because of the shape of the atomic box. It's the shape of the box surrounding the oxygen nucleus. Now, oxygen's got 8 protons and 8 neutrons in its nucleus, which means that it needs 8 electrons filling up its energy levels, and the electrons fill up the energy levels like that. So you get 3 full energy levels, and you get 2 energy levels with a single electron in them. Now, that's kind of makes oxygen a voracious consumer of electrons. It would like, if it can, it's energetically favourable for it to fill up those missing gaps. Hydrogen has 1 proton, and so it has 1 electron sat there in its lowest energy level. Again, it has a space there. It would also like to fill that up. So what happens when I give it a little kick with this splint is that the hydrogen is encouraged to react with the oxygen. It's energetically favourable for it to share its electron. So the oxygen shares with the hydrogen shares with the oxygen. There are 2 gaps, so you get 2 hydrogens that would like to react. In doing so, the rearrangement of those electrons in the energy levels is such a great giver of energy that you saw a flash. All that flash that you saw, the little explosion, was energy being released when the electrons in the hydrogen and the oxygen reconfigure, just like the apple reconfigured itself by dropping to the ground to get into the lowest energy state. 2 hydrogens, 1 oxygen. What does that make? Right, H2O. So that is essentially the reason why we get chemistry. Without Pauli exclusion principle, all the electrons would crowd down into the lowest energy level and there'd be no chemistry, which is worse than it sounds. Because without chemistry, of course, we'd have no magnificent structures in the universe, like water, diamonds, or indeed any of you. Now, there's another consequence of the exclusion principle that wasn't proved actually until 1967, just 1 year before I was born. Pauli's principle says that identical electrons can't occupy the same energy level. This is an absolute requirement. So it also means that electrons will avoid each other at all costs. And that, it was proved, is the actual reason that I don't fall through the empty atoms that make up the floor. That's ultimately what gives the illusion of solidity to the empty world of atoms. And if you think a little bit more deeply about it, and this throws up a bewildering conclusion, and it's this. The Pauli exclusion principle applies to every electron in the universe. Not just every electron in a single atom or a single molecule. And this leads to a bizarre conclusion. The particles that make up this diamond are in communication with particles everywhere. Inside all of you and inside the atoms in the furthest corners of the universe. Let me explain that a little bit more. Pauli exclusion principle says no identical electrons can be precisely the same energy level. What do you have more than 1 atom? For example, in this diamond, there are 3 million billion carbon atoms. So this is a diamond-sized box of carbon atoms. And here's the thing, the Pauli exclusion principle still applies. So all the energy levels in all those 3 million billion atoms have to be slightly different in order to ensure that none of the electrons sit in precisely the same energy level. Pauli's principle holds fast, but it doesn't stop with the diamond. See, you can think of the whole universe as a vast box of atoms with countless numbers of energy levels, all filled by countless numbers of electrons. So here's the amazing thing. The exclusion principle still applies, so none of the electrons in the universe can sit in precisely the same energy level. But that must mean something very odd. See, let me take this diamond and let me just heat it up a little bit between my hands, just gently warming it up. I'm putting a bit of energy into it, so I'm shifting the electrons around. Some of the electrons are jumping into different energy levels. But this shift in the configuration of the electrons inside the diamond has consequences, because the sum total of all the electrons in the universe must respect Pauli. Therefore, every electron around every atom in the universe must be shifting as I heat the diamond up to make sure that none of them end up in the same energy level. When I heat this diamond up, all the electrons across the universe instantly but imperceptibly change their energy levels. So everything is connected to everything else. At the beginning, I promised I'd explain everything in the universe, which I have in some way. But also I said that I'd give you a deeper explanation of that wavy behaviour of the subatomic world. So here it is. In my view, this is the deepest explanation we have, and it's down to the Nobel Prize-winning physicist Richard Feynman, who his colleague Freeman Dyson once described as half genius, half buffoon, but he subsequently, after having worked with him for a while, changed that to all genius, all buffoon. Let's go back to the double-slit experiment. But now, instead of just showing you the pattern, this is Richard Feynman, by the way, instead of just showing you the pattern, I want to show you how that pattern builds up. Remember, we're firing electrons at two slits, almost pouring them through two slits and seeing what happened when they were detected on the other side. Well, this is one electron at a time being fired through the slits and hitting the screen, building up in the pile. Only when the one electron has gone through was another one fired. And you see, this is real data, again, a real movie of that happening, and you see the interference pattern. Electrons, no electrons, electrons, no electrons, the wavy type interference pattern building up. What could be happening there? So here it is again, well, just electrons, and you see that what emerges is that wave-like behaviour. So you might have thought, well, I kind of understand what's going on with the double slits. There's loads of electrons piling through the slits, and somehow there's some interference, just like a big water wave, and you build up the interference pattern. Well, no, because this is one electron at a time. So what could possibly be happening? Well, Feynman was a wonderfully intuitive, logical physicist, no ordinary genius, he was often described as. And he said this: here are the slits, here's the screen, the electrons start off here. What happens? Well, obviously, the particle, the electron, must go through a slit, and it must appear somewhere on the screen. But it needs to be able to interfere with itself. There have got to be regions on the screen where there are no electrons. It's prevented from landing there. So it must at least go through the other slit as well and get to that point. And there must be some mechanism for these paths interfering with each other. But why stop there? See, that wouldn't be particularly logical. Why only let it go through two paths? Why not let it go through that path? Or maybe some sort of path like that? Or maybe like that? Or maybe, indeed, off here and out of this lecture theatre, and then maybe, you know, through Jonathan's head on its way. I've got to say through Paul's foot, haven't I? Because I just have to. Paul foot. I don't know. What a rubbish thing to say. But anyway, you could go through Jonathan, off up Oxford Street, up to Newcastle, indeed, on to the Andromeda Galaxy, and back again, and land at this point on the screen. Why not? Why not allow the particle to travel along every possible path it can from one point to the other? And that is indeed what happens, in the sense that that's the way Feynman's theory works. In principle, it's not too difficult. You just have to calculate some quantity associated with each path and find some mathematical machinery for adding all those things up and seeing whether or not they all interfere together and disappear or appear when they land on the screen. There is a formula that does that, and this is all I really need to say. Let me turn it around. There it is. Thank you and good night. This is called the Feynman path integral, and this just says sum up over all the paths and calculate something that will tell you the probability of an electron going from one place to another. That might look a tremendous mess, or it might look very simple, illuminating. I suppose it depends on your point of view. Probably a tremendous mess, granted, but this formula is just a little machine, and that's a good way to think about it. It takes all the possible paths a particle can have, it adds them up, and it spits out the probability that it'll end up at some particular place. And that includes the particles that make up the diamond. And for the moment, it's sat on its little cushion there. Let me put it back in its box. Now, Feynman's version of quantum theory tells us something rather shocking. This diamond is made up of atoms, and the atoms are behaving according to quantum theory, according to Feynman's equation. In other words, they're all currently exploring the universe, hopping around everywhere, exploring every possible path they can. And that means this diamond is doing the same thing because it's made of atoms. that means there's a finite chance that it will not be inside this box at a later time. You can see where I'm going. But it'll jump completely out of its own accord without me touching it. And that's what I'm going to tell the judge. But what's remarkable is that I can calculate what the chance is by using the simplified version of Feynman's formula. And this is it. See, just by doing a bit of maths, you can work that, simplify it, and turn it into this, which is an expression for the time you would have to wait, on the average, to have a reasonable chance of that diamond hopping out of its box. And it goes like this. Okay, so that is the distance we want it to hop. That is the size of the box. That's the mass of the diamond. And that's something called Planck's constant. Now, I really need another volunteer here because I'm going to actually do the maths, because I want to show you that you can do the sum quite simply. And I believe that Jonathan has kindly agreed to do some sums, so thank you. How's your maths?
Well, you know the art. You know that's easy for me.
Yeah, I do. That's why I asked you. Actually, we're going to do it. So x, right? That's the distance we want the diamond to jump.
Okay.
So let's say the box is about 5 centimeters.
Okay.
So let's say 6 centimeters for x.
Okay.
Right. And the mass of the diamond is 290 something carats. It's about 60 grams.
Roughly, yes.
Right. An expert on diamond. So, first of all, we have to just multiply those three numbers together.
So 6 centimetres by 5 centimetres
Yeah.
by 60 grams.
Yeah, 6 times 5 times 6.
So 30 times 60.
Yeah.
Then you just said 6. Have you reduced that to 60?
60 grams.
Okay. 30 times 6 is 1,800. Is that right? 60?
It's heavy.
Yes. The BBC used to pay me in these. Okay, so that's right.
Then, though, we get to this.
Over the thing.
6.6 times 10 to the minus 34 kilogram meters squared per second. Right? That is Planck's constant. This is a fundamental constant of nature. It's intrinsic to the way the universe is put together. It's like the speed of light, it's like the strength of gravity. It is the fundamental thing, constant if you like, that sets the scale for quantum phenomena. So, there's a slight issue here, because you see that you'll have noticed it.
Yes.
The units are kilograms meters squared per second, and we've calculated the 1,800 in centimetres and grams.
Which, by the way, I'm amazed I got that way.
Yeah. So first of all, we better add another 10 to the minus 2 and a 10 to the minus 2 and a 10 to the minus 3 on. So it's 10 to the minus, 7?
Yeah.
So all you've got to do is divide that by that.
All of that with that?
Divide that by that, roughly.
Roughly? I don't even know what that is. I don't even do... I don't even know that. For me, that's a kilogram. I don't even know.
No, I've done the unit conversion for you. You've just got to divide.
Where's the unit conversion?
1800 times 10 to the minus 7 by 6.6.
I have no idea what you're doing to me and why you want to do this to me.
Help me out.
Maybe
10 to the minus. Well, you got 10 to the minus 34 downstairs. Bring it upstairs. It becomes 10 to the plus 34.
Where do I put it? Up here?
Yeah, put it next to 10 to the minus. So then you got 34 minus 7.
Okay, 34 minus 7.
Yeah.
Yes. Okay, so that's.
So that's 10 to the plus 27.
I really
You've got 10 to the 3.
This is the worst thing that's happened to me as an adult.
We've got 10 to the 27. Okay. Just for any children watching, I should say, 34 minus 7 is 27. So we've got 10 to 27, and then we've got 6, and we've got 1800. So we've got to divide those things so we get about a 3 and another 100.
If you say so.
3, 10 to the 29.
Okay. Ish. Once again, I am none the wiser.
No, you said
why couldn't I have done James May's job where you just set fire to me? And everyone went, ooh! And he's so happy he did that. I'm now sweating.
No, you're done. We're done.
We've done it.
Yeah, so you've calculated. This is what that number is. You calculate. And you see, we just put in the numbers divided by Planck's constant. What this number is the number of seconds you would have to wait on the average to have a reasonable chance of the diamond hopping out of the box on its own.
I could have told you that's not going to happen without any of this. I think the diamond is safe in the box unless it's turned into a dead cat. That's the fear, isn't it?
I'll tell you what this is though. Do you know roughly what that is?
A 9?
10 to the 29.
I don't know what that. Why would I know what it is?
In years.
In years?
Yeah. Well, I'll tell you what it is. It is 600 billion times the current age of the universe.
I don't know what to do. I'm just going to keep smiling.
The point of that is to show really that quantum theory doesn't just apply to the inconceivably small world of the atom. The same rules apply to you, to me, and the diamond. It's just that the objects out here in the familiar world, like the diamond, we don't usually see quantum effects. The reason for that is the smallness of Planck's constant. You see, we had quite a big number here, but we had to divide it by an extremely small number in order to work out the time we'd have to wait, and that's why that's big. See, if that were 1 or something like that, then we wouldn't have had to wait many seconds, about 1800 seconds in fact, or something like that, for the diamond to hop out of the box. So it's Planck's constant, this fundamental constant of nature, that means that quantum theory is rather unfamiliar, because it applies to small things because Planck's constant is small. Now, you could theoretically make the diamond jump sooner. Look again at this equation. One way to do it, as I've said, would be to make Planck's constant very big, but you can't do that. It's a fundamental constant of nature. What you could do, though, is you could shrink the size of the box. So this delta x here. If I made the box smaller and smaller and smaller, I'd make the time I had to wait for it to jump out of the box smaller and smaller and smaller. So this equation says that the more we know the position of something, the position of this diamond in the box, let's say, then the more likely it is for the diamond to jump out of the box. Now this is known as Heisenberg's uncertainty principle. The more you try to pin down a particle's position by trapping it in a smaller and smaller box, the more likely it is to jump around. Now, you might have come across Heisenberg's uncertainty principle. It's one of the most famously misunderstood and misrepresented parts of quantum theory. It says precisely that the more precisely you know a particle's position, the less certain you can be of its momentum. And you can see that it emerged, I derived it from a fundamental equation. It's not complete nonsense, I didn't make it up. It's often misrepresented by what I would call mischievous hippies to mean that physicists are rubbish at their job, or that the equipment is no good and we're unable to measure 2 things about a particle with any accuracy. But Heisenberg's uncertainty principle is a consequence of the laws of quantum theory. It emerges from Feynman's equation. It has nothing to do with any of that wishy-washy, dribbling nonsense. In that spirit, I want to show you that rather than restricting our knowledge of the natural world, Heisenberg can actually widen it. In fact, this rule about the unimaginably small particles can explain some of the most massive and spectacular objects in the universe. I'm going to end by explaining how everything I've told you this evening predicts the existence of diamonds bigger than this. In fact, bigger than this lecture theatre. In fact, diamonds as big as a planet and as massive as a star. Now, to understand how this can be, we need to understand something about the life cycles of the stars themselves. Stars are big clumps of matter collapsing under their own gravity. As they collapse, they heat up, and they set up a chain reaction of nuclear fusion reactions, where the nuclei of hydrogen fuse together, initially to form helium, and eventually they fuse to form carbon and oxygen, and all the heavy elements up to and including iron. That's where the heavy elements come from in the universe. In this process, vast amounts of energy released. That energy creates a pressure that holds the star up and prevents it from collapsing. But stars don't have infinite amounts of fuel. and eventually those fusion reactions must cease. In 5 billion years, this will happen to our sun. It'll stop generating enough energy to prevent its own collapse, and so it will collapse. And by the end of their lives, stars like our sun have converted all the hydrogen in their cores. Mainly, they converted it into oxygen and carbon. Now, remember that those carbon atoms, just like those in our diamond, are almost entirely empty space, so you might expect that the space can be squashed and compressed, almost out of existence as the dying star collapses. But as the star collapses and becomes denser, its electrons get closer and closer together. Finally, they're so close that they try to occupy the same volume of space as each other. Then, Pauli's exclusion principle steps in, because the electrons cannot occupy the same bit of space. They are unable to overlap. So they start to try to arrange themselves such that they have as much space as they possibly can. And you might imagine them as being alone inside little boxes like this. And the boxes shrink and shrink and shrink as the star collapses. But then, as the electrons become more and more confined, Heisenberg's uncertainty principle comes into play. As the electrons' boxes get smaller and smaller, their tendency to hop out of the box becomes greater and greater. So you can think of it that they're frantically vibrating around faster and faster inside these boxes of ever decreasing size. This quantum jiggling exerts a pressure which stops the star from collapsing any further, leaving something called a white dwarf star, which is a densely packed dead star the size of the Earth but the mass of our Sun, and 1 million times more dense than water. See, white dwarfs are so dense that if I was to stand on their surface, the gravitational pull would make me weigh something like 30,000 tons. White dwarfs are strange objects indeed. But here is the final triumph, I think, of quantum theory. It is the most powerful example I know of its power to predict how the natural world behaves. See, it predicts the existence of these strange stars, of white dwarfs. But it does more than that. In the 1930s, the physicist Subrahmanyan Chandrasekhar used quantum theory to predict the maximum mass of a lump of matter that can be held up by the exclusion pressure of electrons to form a white dwarf. He just used the uncertainty principle, essentially, and the exclusion principle. He found that there should be no stars of this type with masses greater than 1.4 times the mass of our Sun. Now, to date, astronomers have found tens of thousands of white dwarf stars, and they have found that not one in the sky exceeds the maximum mass calculated by Chandrasekhar using the simple laws of quantum theory. And in amongst those stars, astronomers have found something that I think is quite extraordinary. Now, that diamond is 296 carats. In the heart of this constellation, Centaurus, which is a few tens of light years away, they've detected a white dwarf star with the wonderful name BPM 37093. As it died and cooled, the carbon within the core crystallised. So BPM 37093, which is somewhere around there, became a diamond, just like this, but of 10 billion trillion carats. We understand in detail why such a thing can exist. That's a diamond, light years away, intimately connected to this diamond, and indeed intimately connected to everything else in the universe by the laws of quantum physics. What a remarkable testament to the power of the wavy behaviour of electrons, and what a spectacular demonstration of the effectiveness of quantum theory. Quantum theory is a uniquely potent tool that gives us our best understanding of how the inconceivably small can give rise to the inconceivably large. It is the most accurate way that we currently possess to understand our universe. It explains how atoms are empty yet solid, how the wave-like behaviour of electrons creates the hardest known substances, and how the real world emerges from subatomic particles that explore the universe, the entire universe, in an instant. There's nothing strange, there's nothing weird, there's no woo-woo. It is just beautiful physics. Thank you.
some of it I could understand, other parts I could not understand. It was so exciting, I loved it.
I love listening to him. He does say, makes it very clear. He speaks kind of just at the right pace for me to absorb it, and also he's got a very winning smile. So even though he does insist on keep telling us how soon it is that the sun's going to die out and we will all die screaming and flying off into the inky void of space, you don't mind it because he looks so sweet when he tells it.
What do you now think of quantum physics?
I feel like I maybe should have stuck in at school a little bit more. But you know, the career that I've chosen is going well. So, but I have learned a lot. Mainly don't volunteer for things.
How are your hands now? No, my hands are fine. All it does is singe the very fine hairs on the back. But I was getting a bit, ignorant anyway, so it's probably not really playing.
That's great, I really loved it. Yeah, I think it was fantastic. It was almost exactly about everything I think about all the time.
There's comedy and chat over on BBC Two tomorrow at 9:30 with the Rob Brydon Show. But next tonight, it's time for Match of the Day 2.
Okay, it seems like you made it all the way to the end. I hope you got something out of it. Remember to give me a thumbs up and share and subscribe. Leave a comment and put the notification bell on. It's really important that you get messages every time I post a video. This is a new channel. The other one was hacked, so I'm trying to rebuild. So give it a thumbs up, share with your friends, and yeah, if you want to support my channel, you can go to my Patreon and become 1 or 5 or whatever type of patron you choose to. For $5 you can actually win a small painting in my Patreon giveaway every month. So with this, see you in the next video, stay cool and keep painting.